Hello there, and welcome to Science for Sleep. I'm glad you're here, settling into this small pocket of calm where curiosity slows down and science takes its time. There's no rush tonight, nothing to solve, nothing to remember, nowhere to be, just a quiet stretch of moments where ideas can drift past gently, like distant lights seen through a window at night. Wherever you're listening from right now, whether the room around you is dark and quiet or softly lit with the last traces of the day, I hope this feels like a place you can rest your attention. Maybe you're lying down, maybe you're sitting somewhere familiar, maybe this is a routine you return to when the day feels a little too full. And out of curiosity, where are you listening from tonight? Is it late where you are or early? Is the world outside still active, or has it begun to slow into that softer nighttime rhythm? Tonight, we're going to spend some time thinking about something very large, not in a dramatic or overwhelming way, but in a slow, grounded way that lets the mind stretch without strain. The subject waiting for us is the Andromeda galaxy, a vast neighbouring collection of stars that exist far beyond our planet, beyond our solar system, beyond even the familiar shape of our own galaxy. When people hear the word galaxy, it can sound distant and abstract, like something meant only for textbooks or telescope images. But galaxies are physical places, made of stars, dust and space, and Andromeda is one of the closest large ones we have. The question we're exploring is a simple one on the surface. How big is the Andromeda galaxy really? Yet, as with many simple questions in astronomy, the answer grows larger the longer you sit with it. Size in space doesn't behave the way size does in everyday life. It isn't something you can measure by stepping from one end to the other or by tracing an outline with your eyes. Galactic size involves distances so large that the brain has to let go of its usual measuring tools and learn a different kind of patience. Before we ease into that, let's slow the pace even more. There's no need to picture anything yet. No diagrams, no glowing spirals, no numbers racing across your thoughts. Just the idea that somewhere beyond the stars you see at night, there is another entire galaxy, quietly existing, moving through space at a speed that is both enormous and, in human terms, unnoticeable. It has been there for billions of years, long before the first humans looked up, and it will remain long after the present moment has passed. If you find this kind of exploration soothing, or if it simply helps your thoughts soften a little, you're welcome to like the video or subscribe to the channel. It helps this space reach others who might be looking for the same gentle balance between learning and rest. There's no pressure though. You can also just listen and let the words pass by, taking nothing with you except a sense of ease. The Andromeda galaxy often enters conversations as a neighbour, a companion drifting through the same region of the universe as we are. That word neighbour can be misleading. In everyday life, neighbours live close enough that you might borrow something from them or wave across a fence. In cosmic terms, neighbours are defined by distances so large that light itself takes millions of years to cross them. Even so, Andromeda is close enough that its light reaches us without needing the most powerful instruments ever built. On very dark nights, far from city lights, it appears as a faint blurry patch in the sky, something easy to miss if you're not looking for it. That small patch of light doesn't hint at what's really there. It doesn't suggest size or structure or scale. It doesn't tell you that you're seeing the combined glow of hundreds of billions of stars stretched across a region of space so wide that writing the number down already feels excessive. And yet, that faint glow is honest. It's not a picture or a simulation. It's light that has travelled across space for more than 2 million years, arriving now at this exact moment while you listen. Thinking about size in astronomy often starts with letting go of comparison. There is no everyday object that works as a reliable reference. Mountains, oceans, continents, even the entire Earth quickly become too small to help. Instead, astronomers rely on distance, on motion, on gravity, on the behaviour of stars and gas over time. When we talk about how big Andromeda is, We're really talking about how far its influence reaches, how widely its stars are spread, and how much space it quietly occupies. The idea of size becomes layered. There is the visible part, the region that shines brightly enough for us to see directly. Then there are the outer regions, faint and thin, made of stars scattered far apart, still moving together under gravity. Beyond that lies an even larger halo of dark matter, invisible but massive, extending far beyond the light. Each layer adds to the answer, and none of them fits neatly into a single number. As we continue, the focus won't be on memorizing distances or definitions. Instead, the goal is to build a sense of scale slowly, the way your eyes adjust to darkness. At first, everything seems black and empty. Then faint shapes begin to appear. With time, the space fills in, not all at once, but gradually. That's the pace we'll keep here. It might help to remember that galaxies are not solid objects. They don't have edges you could bump into. Their boundaries are soft and gradual, defined more by influence than by matter. When astronomers say a galaxy is a certain size, they're choosing a point where its presence fades into the surrounding space. That choice depends on what you're measuring and how sensitive your instruments are. As technology improves, galaxies tend to grow, not because they're changing, but because we're noticing more of them. Andromeda, in particular, has been growing quietly in our understanding for decades. Early observations showed a bright central region and graceful spiral arms. Later studies revealed stars far beyond those arms, scattered like a loose cloud. More recent work has uncovered enormous streams of stars, remnants of smaller galaxies that Andromeda absorbed long ago. Each discovery extended its effective size, stretching the answer further outward. While this might sound complex, there's no need to hold all of it in your mind at once. You can let each idea pass through, settling only as much as it wants to. This isn't a test. It's more like listening to someone describe a landscape while you rest, letting the shape of it form without effort. As the night deepens, or as the day quiets wherever you are, it's worth noticing how different time feels when you're thinking on these scales. Minutes soften. The pressure to move from one thought to the next fades. Galaxies operate on timescales that make urgency irrelevant. Stars take millions of years to drift from one position to another. Entire galactic collisions unfold over spans so long that no single observer could ever watch them happen in full. That slow pace is part of what makes astronomy such a fitting companion for rest. It invites patience. It makes small worries feel less demanding, not because they don't matter, but because they don't need immediate attention in this moment. Right now, the universe is doing exactly what it has always done, whether we watch or not. Let your breathing find its own rhythm. Let the words continue to flow without needing to follow every detail. The story of Andromeda's size doesn't begin with numbers or equations. It begins with a faint light in the sky, a question asked quietly, and the willingness to sit with something vast without trying to contain it. When people hear that the Andromeda Galaxy is our neighbour, it can sound oddly comforting, as if it were something close enough to feel familiar. The word suggests proximity, a quiet presence just beyond what we know, something nearby enough to acknowledge but distant enough to leave alone. In everyday life, neighbours share walls, streets, or at least a horizon. In space, the definition shifts so dramatically that the word almost loses its meaning, yet it remains useful because it hints at relationship rather than closeness. Andromeda exists in the same local region of the universe as we do, bound by gravity to many of the same large-scale structures. It drifts through the same cosmic environment, part of the same loose gathering of galaxies that astronomers call a local group. Within that group, Andromeda and our own galaxy are the two largest members, like two slow-moving islands floating in a vast dark sea. Everything else around them, smaller galaxies, faint clouds of stars and streams of debris, moves in response to their combined gravitational pull. Calling Andromeda a neighbour does not mean it is nearby in any intuitive sense. The distance between us is so great that light itself, the fastest thing we know, takes more than 2 million years to cross it. That means the light reaching your eyes tonight left Andromeda long before modern humans existed. It travelled silently through expanding space, passing nothing familiar until it finally arrived here, thin and faint, carrying information from a time unimaginably distant. Despite that distance, Andromeda is one of the few galaxies visible to the naked eye. Under dark skies, far from city lights, it appears as a soft, elongated blur. It doesn't sparkle or draw attention to itself. It doesn't look large or dramatic. In fact, it's easy to mistake it for a cloud or ignore it entirely. That faint patch is not an illusion or a trick of the atmosphere. It is the combined glow of hundreds of billions of stars compressed into something the eye can barely register. This contrast between appearance and reality is part of what makes Andromeda such a compelling subject. Something so enormous can appear so small. Something so distant can still be seen at all. The darkness between us and Andromeda is not empty in the way a room without furniture is empty. It is filled with space itself, stretching, expanding, carrying galaxies along with it. The fact that Andromeda's light reaches us at all is a reminder that space, while vast, is not infinite in the ways that matter for observation. In the night sky, stars dominate our attention. They are points of light, sharp and immediate, each one a sun in its own right, relatively close on cosmic scales. Andromeda hangs behind them, not part of the star field but layered beyond it. Like a distant landscape glimpsed through a foreground of lights, your eyes instinctively focus on the nearest bright points, leaving the galaxy to linger at the edge of perception. This layering is important. When you look at Andromeda, you are not seeing something located just beyond the stars you recognise. You're looking past them, through the disk of our own galaxy, through clouds of gas and dust, through space shaped by gravity and motion, toward another entire galaxy occupying its own region of the universe. The darkness between here and there is not uniform. It contains faint traces of matter, stray particles, and the subtle pull of gravity that binds the local group together. Andromeda is not stationary. It is moving through space, just as our own galaxy is. The motion is slow by everyday standards but immense in scale. Andromeda and the Milky Way are drifting toward each other, drawn together by gravity. The approach is gentle and gradual, measured in millions of years rather than seconds. Nothing about this motion is urgent. It unfolds on timescales that make patience irrelevant. The idea that something so far away can still be called a neighbour challenges the way we think about space. In a city, neighbourhoods are defined by walking distance. In astronomy, neighbourhoods are defined by gravity. If two galaxies influence each other's motion, if they are bound together over cosmic time, they are considered neighbours regardless of the vast emptiness between them. By that definition, Andromeda is as much a part of our cosmic environment as the Moon is part of Earth's. The darkness that surrounds Andromeda is not a void of nothingness. It is a backdrop against which structure becomes visible. Galaxies form where matter gathers, where gravity slowly pulls gas and stars together. The regions between galaxies appear dark because matter there is thinly spread, not because it is absent. That darkness carries its own quiet information, shaping how galaxies move and interact. From a human perspective, darkness often feels empty or unsettling. In astronomy, darkness is simply space without enough light to stimulate our eyes. It is neutral, neither threatening nor comforting. Andromeda hangs within that darkness, neither approaching quickly nor drifting away, simply existing as it has for billions of years. Its quiet presence does not depend on being observed. Long before telescopes existed, people noticed Andromeda without understanding what it was. Ancient observers recorded it as a small cloud or misty patch in the sky. It didn't behave like a star, it didn't move like a planet. It remained fixed relative to the constellations, quietly persistent. Without the concept of galaxies, there was no reason to imagine it as anything more than a curious smudge. That early uncertainty reflects something important about scale. Our senses evolved to navigate environments measured in meters and kilometers, not in light years. When confronted with objects that exceed those scales, the brain defaults to familiar categories. A faint blur becomes a cloud. A steady point becomes a star. It takes tools and patience to reveal what those categories miss. As telescopes improved, Andromeda slowly revealed itself. The blur resolved into countless individual stars. Spiral structure emerged. Dark lanes of dust appeared, cutting through glowing arms. Each increase in resolution expanded not just the image, but the concept of what Andromeda was. It was no longer a cloud within our galaxy. It was another galaxy entirely, comparable in size and complexity to our own. That realization fundamentally changed our understanding of the universe. It expanded the known cosmos from a single galaxy to a universe filled with countless galaxies. Andromeda became a reference point, a nearby example of what galaxies could be, how large they might grow, and how they might interact. Its status as a neighbour made it accessible in a way more distant galaxies could not be. Yet even as a neighbour, Andromeda remains remote. No spacecraft has ever travelled there. No probe has sampled its stars or crossed its disk. Everything we know about it comes from light, carefully collected and interpreted. That light carries information about motion, composition, temperature and structure. It allows astronomers to map Andromeda in remarkable detail without ever approaching it physically. There is something quietly grounding about that distance. Andromeda exists entirely beyond human influence. Nothing we do here affects it in any meaningful way. Its stars form and die on their own schedule. Its spiral arms rotate at their own pace. Its satellite galaxies orbit and dissolve according to gravity alone. This independence gives Andromeda a kind of stability in the imagination. It is there whether we pay attention or not. When you think about Andromeda hanging beyond the stars, it helps to imagine depth rather than distance. The sky is not a flat dome with objects pinned to it. It is a layered space extending outward in all directions. Stars sit at different depths. Nebulae occupy others. Andromeda lies far beyond most of what we can see, a background structure faintly visible through everything else. Depth perception is something our eyes struggle with at night. Without familiar size cues, distance becomes ambiguous. A bright star could be relatively close or extremely far. Andromeda's faintness does not indicate small size. It indicates enormous distance. In fact, if Andromeda were closer, it would dominate the sky, stretching across a vast area, brighter than any constellation. The darkness between us and Andromeda also acts as a kind of time buffer. Because light takes time to travel, looking at Andromeda is an act of looking into the past. You're not seeing it as it is right now, but as it was millions of years ago. The galaxy has continued to evolve since then, stars forming and dying, structures shifting subtly. The image reaching us is a delayed message. This time delay is not unique to Andromeda. It applies to everything we see in space. Even the light from the sun is 8 minutes old by the time it reaches Earth. The difference with Andromeda is the scale. Millions of years stretch beyond everyday intuition. Human history fits entirely within that gap many times over. Despite this, Andromeda's overall structure remains stable on those timescales. Galaxies evolve slowly. While individual stars change and gas clouds move, the galaxy as a whole retains its shape for billions of years. That stability allows astronomers to treat the image we see as a reliable representation of its current form, even knowing it is technically outdated. The idea of a neighbour hanging quietly beyond the stars invites a shift in perspective. It suggests that the universe is not a chaotic scatter of unrelated objects, but a structured environment with relationships and patterns. Galaxies gather in groups, groups gather in clusters. Clusters form vast filaments separated by enormous voids. Andromeda's position reflects that structure. Within the local group, Andromeda plays a central role. Its mass influences the motion of smaller galaxies nearby. Some orbit it directly, others follow paths shaped by the combined gravity of Andromeda and the Milky Way. The group itself drifts through space, part of an even larger structure stretching across millions of light years. Understanding Andromeda as a neighbour also sets the stage for understanding its size. Size in astronomy is not just about how far something stretches, but about how much influence it has. A galaxy's gravity extends far beyond its brightest stars. Its presence is felt in the motion of other galaxies, in the paths of gas clouds, in the shape of space around it. Long before telescopes, long before written records of astronomy as a science, humans were already looking up. The night sky was not a backdrop or a decoration. It was a presence. It marked time, guided travel, shaped stories, and quietly invited questions that had no immediate answers. Among the countless points of light that appeared after sunset, there was something unusual that some observers noticed, even if they did not yet know what they were seeing. It was not bright. It did not move. It did not sharpen into a point the way stars did. Instead, it lingered as a faint blur, easy to overlook and even easier to forget if you were not paying close attention. On nights when the sky was especially dark, far from fires and settlements, this small patch appeared again and again in the same region. It did not flicker, it did not wander, it simply stayed. At first, there was no reason to think it was anything special. Human vision is sensitive to patterns, but it also fills in gaps and smooths over irregularities. A faint smudge could be dismissed as thin cloud, mist, or even a trick of tired eyes. In a sky filled with moving planets, changing phases of the moon, and the reliable rotation of stars, something that did nothing was easy to ignore. Yet some people did notice it, not because it demanded attention, but because it quietly resisted explanation. It did not behave like a star. Stars appeared as points, sharp and well-defined even when faint. This object did not. It looked soft, diffuse, almost like breath on glass. It was visible only under the right conditions, when the sky itself cooperated. The first humans who noticed this smudge did not have a concept of galaxies. They did not think in terms of star systems or cosmic structures. Their universe was intimate, populated by lights that seemed close enough to influence daily life. The idea that there could be entire collections of stars far beyond the visible ones was not part of any framework available to them. Instead, early observers worked with what they had. They grouped lights into patterns, told stories about them, and used them as markers for seasons and directions. The smudge did not fit neatly into these systems. It did not belong to a constellation. It did not rise and set differently from the surrounding stars. It did not signal anything obvious. In ancient records, references appear to a cloudy patch or a little cloud in the sky. These descriptions were careful and restrained. There was no claim that it was enormous or distant. It was simply noted as unusual, something that existed reliably without explanation. This restraint is important. Early astronomy was observational rather than interpretive. People recorded what they saw, not what they imagined might be behind it. Without tools to magnify or resolve detail, speculation was limited by necessity. The smudge was described as a cloud because that was the closest familiar category that matched its appearance. As centuries passed, the smudge remained where it was. Generations came and went. Cultures rose and fell. The sky changed only subtly over long periods, reinforcing the idea that it was stable and unchanging. The smudge became part of that stability, a quiet constant in the northern sky. In regions with frequent clouds, smoke, or artificial light, it may have gone unnoticed entirely. Its visibility depended on darkness. This meant that awareness of it varied by location and lifestyle. People who spent more time outdoors at night, far from settlements, were more likely to encounter it. Others might never have seen it at all. Even when it was seen, there was no urgency to explain it. Astronomy was woven into daily life through calendars and navigation, not through cataloguing every anomaly. The smudge did not interfere with planting, travelling, or predicting seasons. It did not demand interpretation. As written traditions developed, some observers began to document it more formally. They included it in lists of fixed sky objects, noting its position relative to known stars. These records preserved the fact that something unusual existed there, even if its nature remained unclear. Still, nothing about these early observations hinted at the true scale of what was being seen. The smudge did not look large. It did not dominate the sky. It was subtle enough that it could vanish entirely under even modest light pollution or moonlight. Its appearance offered no clues about distance. This limitation of human vision shaped understanding for centuries. Without magnification, all extended objects in the sky tended to blur together conceptually. Nebulae, star clusters, and galaxies were all grouped under the same vague category of cloudy objects. There was no clear way to separate one from another. The invention of the telescope changed many things, but not immediately. Early telescopes were crude by modern standards. They magnified objects, but often introduced distortions and chromatic effects. When pointed at the smudge, they revealed more structure, but not enough to solve the mystery. Instead of resolving into points of light the way star clusters did, the smudge remained stubbornly diffuse. It grew larger in the field of view, showing variation in brightness, but it did not break apart cleanly. This was puzzling. Many cloudy objects, when magnified, resolved into stars. This one resisted. Some observers interpreted this resistance as evidence that the smudge was made of glowing material rather than stars. It was classified alongside other nebulae, thought to be clouds of luminous substance within the boundaries of our own galaxy. This explanation fit comfortably within the prevailing view of the universe as a single star-filled system. At the time, the idea that the universe might contain many galaxies was not seriously considered. The Milky Way was thought to be the entire cosmos, a vast but finite collection of stars surrounded by emptiness. Anything visible in the sky was assumed to belong to it. The smudge then was folded into that assumption. It was a nebula, a cloud, perhaps a region where stars were forming or light was scattering. There was no reason to think otherwise. It occupied a known location, moved with the rest of the sky, and showed no obvious signs of being fundamentally different. What is striking in hindsight is how long this interpretation persisted. For centuries, the smudge was observed, sketched, catalogued, and discussed without anyone realizing its true nature. This was not due to lack of intelligence or curiosity. It was due to scale. The true size and distance of the object lay far beyond what existing tools could reveal. Human intuition struggles with extremes. Very large distances compressed into the same mental category as moderately large ones. Without a reference, millions of light years feel no different from thousands. The smudge offered no internal scale markers. Its stars were too far away to appear individually, even through early telescopes. As observational techniques improved, details began to emerge slowly. Dark lanes appeared, cutting across the glow. The shape suggested structure rather than randomness. There was a hint of symmetry, a faint sense that this was not just a cloud, but something organized. Even then, interpretation lagged behind observation. New details raised new questions, but the prevailing framework still held. The smudge was placed within the Milky Way, assumed to be part of the same vast star system that included the Sun. It was not until astronomers began to measure distances to stars more accurately that cracks appeared in this view. Certain variable stars acted as markers, allowing observers to estimate how far away they were based on how their brightness changed over time. When these stars were identified within the smudge, the results were unsettling. The distances implied by these measurements were far too large for the smudge to be inside the Milky Way. They placed it well beyond the boundaries of the known star system. This was not a small adjustment. It required a fundamental shift in how the universe was understood. The smudge was no longer a cloud within our galaxy. It was another galaxy entirely, comparable in size to our own, composed of countless stars spread across an enormous region of space. What had appeared as a faint blur was revealed to be one of the largest structures in the local universe. This realization transformed the smudge from a curiosity into a cornerstone of modern astronomy. It marked the moment when the universe expanded from a single galaxy to a vast collection of galaxies, each occupying its own region of space. The smudge became a gateway to a much larger cosmos. Looking back, it is humbling to consider how unassuming this discovery began. There was no dramatic flash, no sudden revelation visible to the naked eye. The same faint blur had been there all along, quietly waiting for tools and ideas to catch up. The first humans who noticed it could not have imagined its true nature. They did not fail to understand it. They simply lived at a time when understanding on that scale was not yet possible. Their careful observations laid the groundwork for later insight, even if they did not realize it. This gradual unfolding of the knowledge mirrors the way understanding often grows. It does not arrive all at once. It accumulates quietly, observation by observation, question by question. The smudge in the sky remained the same. What changed was our ability to interpret it. Even today, when we know that the smudge is a massive galaxy, its appearance has not changed. It is still faint. It still requires dark skies. It still does not announce its scale to casual observers. Knowing what it is does not make it easier to see. There is something grounding in that. The universe does not adjust itself to our knowledge. Objects do not become brighter or larger because we understand them better. They remain what they are. Our perspective shifts instead. When people first learn how far away Andromeda is, the number often lands without meaning. It sounds impressive, maybe even absurd, but it does not immediately connect to experience. Saying that Andromeda is more than 2 million light-years away feels similar to saying a phone number out loud. The digits are clear, but the reality behind them remains distant, almost abstract. This isn't a failure of attention or intelligence. It's a limit built into how the human mind handles distance. Distance, as we know it, evolved to be practical. It helps us judge how far to walk, how long it takes to travel, how close something is to reaching us. These judgments work well within the scale of daily life. A few meters, a few kilometers, even a few thousand kilometers can still be framed in terms of travel time, fuel, or effort. Beyond that, intuition begins to soften. Beyond the size of Earth itself, distance becomes symbolic rather than physical. Andromeda sits far beyond that boundary. To say it is about 2.5 million light-years away means that the light leaving it today will not reach Earth until millions of years in the future. More importantly, the light we see now left Andromeda before humans had language, before cities, before agriculture. That light began its journey when early ancestors were still shaping stone tools. Every image of Andromeda is an ancient message that has been travelling through space for longer than our entire recorded history. A light year itself already stretches understanding. It is not a measure of time but of distance, defined by how far light travels in 1 year. Light moves incredibly fast, about 300,000 kilometres every second. Even so, it takes more than 8 minutes to reach Earth from the Sun. That gap alone can feel surprising. Multiply that distance by 60,000 to reach the nearest stars, and then multiply again by hundreds to reach Andromeda, and the scale begins to slip beyond mental grip. Trying to imagine travelling to Andromeda using familiar ideas does not help much. Even at the speed of the fastest spacecraft humans have ever built, the journey would take tens of millions of years. At the speed of light, which no object with mass can reach, it would still take millions of years. These numbers don't invite imagination so much as they resist it. The brain searches for anchors and finds none. This resistance is what makes distance in astronomy so disorienting. There is no gradual slope from here to there. There is an enormous gulf of space that does not behave like terrain. Nothing marks the way. No landmarks pass by. Between the Milky Way and Andromeda lies a region so empty that it defies everyday language. It is not empty in the sense of a room with nothing in it. It is empty in the sense that matter is spread so thinly that even entire solar systems could drift for millions of years without encountering anything substantial. The space between galaxies is part of what makes the universe feel larger than it is crowded. Galaxies themselves are vast, but they are separated by distances that dwarf their own size. Andromeda is not just far because it is big. It is far because space itself stretches enormously between large structures. When astronomers say Andromeda is about 2.5 million light-years away, that number is not guessed. It is measured, carefully and repeatedly, using a chain of methods that build outward from closer distances. These methods rely on objects whose brightness or behaviour is well understood. By comparing how bright those objects appear from Earth to how bright they are known to be, astronomers can infer distance. One of the most important tools for measuring Andromeda's distance involves certain types of stars whose brightness changes in a predictable way. These stars pulse, growing brighter and dimmer over regular intervals. The length of that cycle is directly related to how luminous the star truly is. By observing the cycle and measuring how faint the star appears, astronomers can calculate how far away it must be. When these stars were identified in Andromeda, the results were striking. The distances calculated placed them far outside the Milky Way. This was not a small discrepancy. It was a dramatic shift that forced astronomers to accept that Andromeda was not nearby at all. It was an entirely separate galaxy, located far beyond the boundaries of our own. Distance, at this scale, does more than separate objects. It changes how we perceive size, brightness, and motion. Andromeda appears faint not because it lacks stars, but because its light is spread across such a vast distance. If Andromeda were closer, it would appear enormous in the sky, stretching across many times the width of the moon. Its faintness is the price of its remoteness. This is where distance begins to break the mind. The same object can be unimaginably large and barely visible at the same time. These two facts feel incompatible when approached with everyday logic. Something that large should look large. Something that faint should be small. Space does not follow those rules. The distance to Andromeda also complicates the idea of now. When you look at a tree outside your window, you're seeing it almost as it is. The delay between light leaving the tree and reaching your eyes is negligible. When you look at Andromeda, you are seeing it as it was millions of years ago. There is no way to know its exact current state. Any change happening there now will not be visible from Earth for an equally long time. This delay does not mean Andromeda has changed dramatically since the light left it. Galaxies evolve slowly. Over a few million years, their overall structure remains largely the same. Still, the idea that every observation is a glimpse into deep time adds another layer of distance. Andromeda is not just far away in space, it is far away in time. The human mind tends to collapse space and time into a single idea of distance. Far away often feels like long ago. Close feels immediate. In astronomy, this blending is accurate in a literal sense. Distance and time are inseparable when dealing with light. The farther you look, the older the image becomes. This can be unsettling if you linger on it too long. It suggests that the universe we observe is a patchwork of different eras, layered across the sky. Nearby stars show us the recent past. Distant galaxies show us a much older universe. Andromeda sits somewhere in between, close enough to feel familiar, distant enough to remind us that familiarity is relative. Even the number itself, 2.5 million light-years, does not fully capture the reality. That distance is measured from centre to centre. The outer regions of Andromeda extend farther. Its halo of stars and dark matter stretches well beyond what we can easily see. Some parts of Andromeda are closer to us than others, though the difference is small compared to the total distance. When astronomers refine these measurements, they do so not because the distance is changing in any meaningful way, but because precision matters. Knowing how far away Andromeda is allows scientists to determine how large it must be, how massive it is, and how fast it is moving. Distance is the key that unlocks scale. Without accurate distance, size becomes guesswork. A nearby small object can look the same as a distant large one. Only by knowing how far Andromeda is can astronomers translate its apparent size into physical dimensions. That translation is where the true enormity begins to emerge. The difficulty of grasping distance is compounded by how rarely we encounter true emptiness. On Earth, even the most remote places contain air, gravity, sound, and reference points. In intergalactic space, these cues vanish. There is no medium to slow light, no friction, no landmarks. Motion happens without sensation. Distance accumulates without experience. This lack of experience is why numbers alone fail to convey meaning. Saying that Andromeda is millions of light years away does not trigger any physical memory or emotional response. The mind cannot attach it to anything it has felt before. Instead, it floats as an idea without weight. One way people try to make sense of this is through analogy, but analogies have limits. Scaling the universe down to familiar sizes often distorts relationships. A model that fits in a room cannot capture the emptiness between galaxies without losing detail. A model that preserves distance loses visibility of objects entirely. The mind wants compression. It wants to simplify. Space resists this. The true distances involved are too large to compress without breaking the picture. This is why learning about astronomy often comes with a sense of vertigo. The more you understand, the harder it becomes to imagine. Andromeda's distance also plays a role in how stable it appears. From Earth, it seems fixed against the background of stars. Its motion is too slow to detect without precise instruments. In reality, Andromeda is moving toward us at hundreds of kilometers per second. The distance is so vast that this motion barely registers visually. Over millions of years, that motion matters. Over a human lifetime, it does not. This mismatch between cosmic motion and human timescales reinforces the sense that Andromeda is static and eternal. Distance smooths out change. The same distance that breaks intuition also provides safety. Andromeda's immense mass and gravitational influence do not threaten us now, because space keeps us apart. Gravity weakens with distance. The separation between galaxies allows them to coexist without immediate interaction. Understanding how far away Andromeda really is creates a foundation for understanding its size. The two ideas are inseparable. Size without distance is meaningless. Distance without size is incomplete. Together they form the context in which Andromeda exists as a physical object, rather than a faint patch of light. The focus will gradually shift from how far Andromeda is to what that distance implies. If something appears as large as it does from so far away, what must its true dimensions be? How much space does it occupy? How many stars does it contain? When we say that a galaxy is big, it's tempting to imagine something with a clear edge, a boundary you could trace, a place where it stops and something else begins. That instinct comes from living in a world of solid objects. A house has walls, a city has limits. Even a continent, though irregular, has coastlines that mark where land ends and ocean begins. Galaxies do not work that way, and this difference is where much of the confusion about size begins. A galaxy is not a single object in the way a planet or a mountain is. It is a system, a vast collection of stars, gas, dust, and invisible matter, all bound together by gravity. The components move independently, orbiting a shared centre, drifting, forming, dispersing, and interacting over immense periods of time. There is no sharp line where this system suddenly ends. Instead, there is a gradual thinning, a slow fade from dense regions into sparsity. So when astronomers talk about how big a galaxy is, they first have to decide what they are measuring. Are they measuring the region where stars are densely packed and clearly visible? Are they including the faint outer stars that drift far beyond the bright core? Are they accounting for the enormous halo of dark matter that extends even farther, shaping motion without emitting light? Each of these choices leads to a different answer. This is not a flaw in astronomy. It is an honest reflection of how nature organises itself. Many natural systems lack clear boundaries. A forest does not abruptly stop at the last tall tree. It transitions into shrubs, then grass, then open land. A storm system fades gradually rather than ending at a precise line. Galaxies behave in a similar way, but on scales that make the transitions hard to visualize. In everyday language, big usually refers to physical extent. Something big takes up a lot of space. In astronomy, size can also refer to mass, influence, and reach. A galaxy might not appear visually large, but its gravitational pull could extend far beyond its brightest regions. In that sense, its effective size includes areas where little light exists, but where motion is still controlled by the galaxy's mass. This is why size in astronomy often comes with qualifiers. You may hear about the visible disk of a galaxy, the stellar halo, the gaseous envelope, or the dark matter halo. Each describes a different component, layered over the others, each contributing to the whole. None of them exist in isolation. Together they define what the galaxy truly is. To understand this more clearly, it helps to think about the way light behaves. Stars shine brightly, but their light spreads out as it travels. In dense regions, many stars overlap in brightness, creating luminous structures like spiral arms and central bulges. As you move farther from the center, stars become more spread out. Their combined light grows fainter until it blends into the background of space. There is no moment where stars suddenly stop existing. Instead, they become harder to detect. Early observations of galaxies were limited by this fact. Telescopes could only see the brightest regions. As instruments improved, astronomers began detecting stars farther and farther out. With each improvement, galaxies appeared to grow. This growth was not physical. The galaxies were always that large. What changed was our ability to see them. This is an important point, because it means that any statement about a galaxy's size is partly a statement about observation. Size depends on how faint an object you can detect and how patiently you look. Gas behaves in a similar way. Galaxies contain vast amounts of gas, much of it invisible to the eye. Some of it emits radio waves or other forms of radiation that require specialized instruments to detect. This gas often extends well beyond the regions where stars are common. Including it adds another layer to a galaxy's size. Then there is dark matter. Dark matter does not emit, absorb, or reflect light, but its presence is inferred from its gravitational effects. Stars orbit galaxies faster than visible matter alone can explain. Gas clouds move in ways that suggest additional mass. The most consistent explanation is a halo of dark matter enveloping the galaxy. This halo is enormous. It extends far beyond the visible components, sometimes several times farther than the region containing most of the stars. When astronomers include the dark matter halo in size estimates, galaxies become vastly larger than they appear in images. In this sense, much of a galaxy's size is invisible. This layered structure makes it difficult to answer a simple question like how big a galaxy is. The answer depends on whether you're talking about light, matter, or influence. Each tells a different part of the story. There is also the question of shape. Many people picture galaxies as flat disks with spiral arms like glowing pinwheels. While this is a useful approximation, it oversimplifies reality. Galaxies are three-dimensional. Their disks have thickness. Their halos extend above and below the plane. Their shapes can be warped, stretched, or disturbed by interactions with other galaxies. Because of this, size cannot be captured by a single diameter in the way you might measure a circle. Astronomers often describe galaxies using several dimensions, such as the radius of the disk, the extent of the halo, and the scale over which gravity dominates. These dimensions do not align neatly. Time also complicates the idea of size. Galaxies are not static. They grow by forming new stars, by pulling in gas and by merging with smaller galaxies. Streams of stars, remnants of past mergers, can extend far beyond the main body, tracing ancient interactions. Including these streams changes the effective size of the galaxy. At the same time, galaxies lose material. Stellar winds, supernova explosions, and interactions with other galaxies can push gas outward. Some stars are flung into intergalactic space. These processes blur boundaries even further. A galaxy's size at one moment is not exactly the same as its size at another. This dynamism makes size a snapshot rather than a permanent property. When astronomers give a size for a galaxy, they are describing its current state as best they can measure it. That state reflects billions of years of evolution. The difficulty of defining size becomes especially clear when comparing galaxies. Two galaxies might have similar visible sizes but very different masses. One might be densely packed with stars, while another is more diffuse. One might have a massive dark matter halo, while another's is smaller. Calling one bigger than the other requires specifying what aspect you are comparing. This is why astronomers are careful with language. They might say one galaxy has a larger stellar disk, while another has a more massive halo. Each statement is precise within its context. Without that context, size comparisons can be misleading. When applied to Andromeda, these issues become central. Andromeda appears large in the sky relative to other galaxies because it is both large and relatively close. But its true size depends on how far out you trace its stars and how much of its halo you include. Understanding what we mean by big also requires letting go of the idea that size implies importance or dominance. In space, large objects do not necessarily behave dramatically. Andromeda does not loom or threaten. It simply exists, following the rules of gravity and motion. The human tendency is to associate size with impact. On Earth, large objects are often more powerful or dangerous. In the universe, size operates differently. Immense systems can be quiet. Vast distances can be calm. A galaxy can span hundreds of thousands of light years without doing anything sudden or violent. This calmness can be grounding. It reframes bigness not as something overwhelming, but as something steady. Andromeda's size does not demand attention. It unfolds slowly, visible only to those who take the time to look and think. Another source of confusion comes from perspective. From Earth, Andromeda appears small because it is far away. Its apparent size on the sky does not reflect its true dimensions. This disconnect between apparent size and physical size is fundamental to astronomy. The Moon and the Sun appear roughly the same size in the sky, even though the Sun is vastly larger. This is because the Sun is also much farther away. Andromeda follows the same principle. Its faint smudge spans a few degrees of sky, but those degrees correspond to an enormous physical span at its distance. This translation from angular size to physical size requires accurate distance measurements. Without knowing how far away Andromeda is, astronomers could not determine how wide it truly is. Once distance is known, apparent size becomes meaningful. Yet even then, the edges remain uncertain. How faint a star do you include? How far out does gravity still bind material to the galaxy? These questions do not have single answers. They are matters of definition. This is why scientific discussions of size often involve ranges rather than exact figures. A galaxy might be described as having a stellar disk about a certain width, with a halo extending several times farther. These ranges acknowledge uncertainty without undermining understanding. For someone listening quietly, letting these ideas pass by, it's not necessary to hold on to specific numbers. What matters more is the shift in perspective. Big, in a galactic sense, does not mean easily seen or clearly bounded. It means extended, influential, layered, and gradual. As we continue exploring Andromeda, this understanding of size will become increasingly important. When we say Andromeda is larger than the Milky Way, or comparable, or more massive, Those statements rest on these definitions. They are not casual claims. They are carefully constructed conclusions based on how size is understood in astronomy. The idea of bigness here is not meant to impress, it is meant to orient. It helps place Andromeda within the broader structure of the universe and within our own conceptual framework. It reminds us that familiar words carry different meanings at different scales. As the focus shifts next toward how Andromeda stretches across space in ways we cannot see with our eyes, this groundwork becomes useful. The question is no longer just how far away it is or what it looks like, but how much space it truly occupies when all its components are considered. When you look up at the night sky and manage to spot Andromeda, what you see feels modest, a soft, pale smear against the darkness, something you could easily mistake for a thin cloud or ignore altogether if you were not specifically searching for it. That visual impression is honest, but it is also deeply incomplete. What your eyes register is only the brightest and densest portion of a structure that extends far beyond what human vision can capture. Human eyes are remarkable, but they are tuned for survival on Earth, not for surveying the universe. They are sensitive within a narrow range of light and struggle with low contrast. In dark conditions, they sacrifice detail for sensitivity, blurring faint features together. This trade-off allows us to see stars at all, but it also hides the true extent of objects like Andromeda. The part of Andromeda visible to the naked eye is its central region, where stars are packed closely enough that their combined light stands out against the background. This region forms a bright core and hints of elongated structure. Even this visible portion already spans several times the apparent width of the moon in the sky, though its faintness makes that difficult to notice without careful observation. What lies beyond that visible core is where scale begins to unfold quietly. Surrounding the bright centre are spiral arms, sweeping arcs of stars, gas and dust that curve outward. These arms are not solid bands. They are regions where star formation has been more active, where gas clouds have collapsed and ignited new stars. Between them lies darker space, still filled with stars, just more sparsely distributed. To the eye, most of this structure disappears. The contrast is too low, the light too thin. But instruments that collect a light over long periods reveal these arms stretching much farther than the faint blur suggests. With enough exposure time, Andromeda grows. Its shape becomes clearer, its size increases. Even then, the spiral arms are not the end. Beyond the main disk lies a vast stellar halo, a roughly spherical distribution of stars extending far above and below the plane of the galaxy. These stars are old, dim, and widely spaced. Individually, they contribute almost nothing to the galaxy's brightness as seen from Earth. Together, they mark an enormous extension of Andromeda's reach. This halo is invisible to casual observation. It does not glow, it does not outline itself. It reveals its presence only through careful analysis, through long exposures and sensitive detectors. When astronomers began mapping these outer stars, Andromeda's size expanded dramatically in scientific understanding. What had once been thought of as a disk, perhaps 100,000 light-years across, became something much larger. The halo alone stretches hundreds of thousands of light-years from the centre. In some directions it extends even farther, shaped by past interactions and mergers with smaller galaxies. These interactions leave behind streams of stars, elongated trails that arc through space. They are the remnants of smaller galaxies that wandered too close and were pulled apart by Andromeda's gravity. Their stars now orbit the larger galaxy, tracing faint, graceful paths that extend far beyond the visible disk. To the eye, these streams do not exist. They are too faint, too thin, too diffuse. Yet they are real. They occupy space. They move. They add to the physical size of the galaxy. Ignoring them would be like ignoring the outer suburbs of a city because they are quieter than the centre. Gas adds another invisible layer. Andromeda is surrounded by vast clouds of gas, much of it hydrogen, extending well beyond the stellar disk. Some of this gas is cool and dense enough to form new stars. Some of it is hot and tenuous, interacting with the surrounding intergalactic medium. This gaseous envelope is difficult to detect directly, especially in visible light. It reveals itself through radio observations and through subtle absorption features in the light of more distant objects. Including this gas increases Andromeda's effective size again, pushing its boundaries farther outward. Then there is dark matter, the largest and most elusive component. Dark matter does not emit light, so it cannot be seen directly at any wavelength. Its presence is inferred from how stars and gas move. In Andromeda, as in other galaxies, outer stars orbit faster than visible matter alone can explain. This behaviour points to an enormous halo of unseen mass enveloping the galaxy. This dark matter halo is immense. It extends far beyond the stars and gas, defining the true gravitational boundary of the galaxy. In terms of influence, this halo is what makes Andromeda as large as it is. Objects within this region are bound to the galaxy. Beyond it, they drift more freely through space. When this halo is included, Andromeda's size reaches staggering proportions. The distance from one side of the halo to the other can approach 1,000,000 light-years. That means Andromeda's influence fills a volume of space comparable to the distance between it and the Milky Way. This is where the idea of stretching across the sky becomes especially misleading. From Earth, Andromeda occupies a small patch. In reality, if human eyes could detect all of its components equally, Andromeda would dominate the night sky. It would span a vast area, overlapping constellations, reshaping the familiar patterns of stars. The reason this does not happen is not because Andromeda is small. It is because its light is thinly spread. The brightness of an object depends not just on how much light it emits, but on how concentrated that light is when it reaches us. Andromeda's light is diluted by distance and by sheer size. This dilution is why longer exposures reveal more. A camera that collects light for hours can gather photons that arrive one by one, building an image the eye cannot form in real time. These images show Andromeda as it truly stretches, its outer regions emerging slowly from darkness. Even then, the images are selective. They highlight certain wavelengths. They enhance contrast. They reveal structure by amplifying signals the eye ignores. Each image is an interpretation as much as a record, shaped by choices about what to emphasize. This does not make the images misleading. It makes them informative. They teach us that the sky contains far more than what appears at first glance. They show that apparent emptiness often hides vast structures waiting to be detected. The fact that Andromeda stretches across the sky in ways our eyes cannot see is a reminder that vision is not the same as presence. Something can occupy enormous space without announcing itself. In the universe, subtlety often accompanies scale. This subtlety also explains why early astronomers underestimated galactic size. Without sensitive instruments, they saw only the brightest parts. They had no reason to suspect that faint stars extended so far beyond. The galaxy's true dimensions were effectively invisible. As instruments improved, boundaries kept moving outward. Each new detection pushed the perceived edge farther away. This process has not fully stopped. Even now, astronomers continue to refine maps of Andromeda's outskirts, discovering new streams, new extensions, new hints of structure. This ongoing expansion of understanding does not mean Andromeda is growing rapidly now. It means our picture of it is becoming more complete. The galaxy itself has been large for a very long time. We're simply learning how to see it. There is something quietly humbling in this. It suggests that much of the universe exists beyond immediate perception. What we see is a surface impression, shaped by the limits of our senses. Beneath that surface lies complexity and scale that require patience and technology to uncover. Thinking about Andromeda stretching across the sky invisibly can also change how you think about darkness. The dark regions between stars are not empty in a simple sense. They are full of faint light, scattered matter, and unseen mass. Darkness is often a sign of limitation rather than absence. This idea applies not just to Andromeda, but to the universe as a whole. Galaxies fill space with extended halos that overlap and interact subtly. The boundaries between them are not sharp lines, but regions of gradual transition. Space is structured, but gently so. As Andromeda moves through this environment, its extended components interact with those of neighbouring galaxies. Gas exchanges, tidal effects, and gravitational influences occur long before visible disks touch. These interactions shape the galaxy's outskirts, stretching and warping them over time. All of this contributes to size in a way that defies simple measurement. Andromeda is not a glowing disk floating in isolation. It is a layered system with reach and influence far beyond what first impressions suggest. If Andromeda stretches so far, how does it relate to our own galaxy? Are these invisible extensions unique, or are they common? Does Andromeda occupy more space than the Milky Way, or are they similar in scale? At some point, once Andromeda has stopped feeling like a distant blur and started to feel like a real place, the mind naturally drifts toward comparison. It's difficult not to do this. Comparison is one of the primary ways humans make sense of scale. We understand the unfamiliar by setting it beside something we already know. In this case, the familiar reference is the Milky Way, the galaxy that contains our Sun, our planet, and everything we've ever directly experienced. Comparing Andromeda to the Milky Way does not require rivalry or ranking. It isn't about deciding which galaxy is better, more impressive, or more important. Instead, it's a quiet exercise in orientation. By placing the two side by side conceptually, their sizes, structures, and similarities begin to feel more tangible, even if the numbers themselves remain large. The first thing to recognize is that the Milky Way and Andromeda are broadly similar kinds of galaxies. Both are spiral galaxies, meaning they have rotating disks of stars with spiral patterns winding outward from a central region. Both contain hundreds of billions of stars. Both are embedded in vast halos of dark matter. In many ways, Andromeda is the closest large-scale analogue we have to our own galaxy. This similarity is part of what makes Andromeda so valuable to astronomers. Studying the Milky Way from inside is difficult. We are embedded within its disk, surrounded by stars and dust that block long sight lines. It's like trying to map a forest while standing deep among the trees. Andromeda, on the other hand, presents itself from the outside. We can see its overall shape, its spiral structure, and its distribution of stars in a way that is impossible for our own galaxy. That external view makes comparison tempting, but also tricky. We know the Milky Way best in parts. We know Andromeda best in whole. Any comparison has to account for this asymmetry. Even so, enough is known about both galaxies to draw careful, measured contrasts. One of the most common questions is which galaxy is bigger. The answer depends, as always, on what is being measured. If you compare the visible stellar disks, Andromeda appears slightly larger. Its disk spans roughly 200,000 light-years from one side to the other, while estimates for the Milky Way's disk tend to fall closer to 100,000 to 150,000 light-years. This difference is not dramatic in relative terms. Both disks are enormous by any reasonable standard. Still, Andromeda's visible disk does extend farther, with spiral arms that reach out into space more prominently. This alone does not tell the full story, but it is often the first metric people encounter. Looking beyond the bright disks complicates the picture further. Both galaxies possess extensive stellar halos, regions populated by older, dimmer stars that orbit far from the galactic centre. In Andromeda, this halo has been mapped in remarkable detail, revealing a structure that extends hundreds of thousands of light-years outward. The Milky Way's halo is harder to map from within, but evidence suggests it is similarly extensive, though possibly somewhat smaller. Dark matter adds another layer of uncertainty. The dark matter halos of both galaxies are immense and overlapping in scale. Some studies suggest Andromeda's dark matter halo is more massive than the Milky Way's. Others place them closer to parity. These differences arise from how the halos are modelled and how satellite galaxies move under their influence. Mass, rather than size alone, is another way to compare galaxies. Mass includes stars, gas, dust, and dark matter. In this category, Andromeda often comes out slightly ahead. Many estimates place Andromeda's total mass at roughly 1.5 to 2 times that of the Milky Way. This additional mass influences how the two galaxies interact gravitationally. That gravitational interaction is not theoretical. Andromeda and the Milky Way are moving toward each other. Their mutual pull is strong enough to overcome the expansion of the universe at this scale. This motion implies that Andromeda's mass is substantial, comparable to or exceeding that of our own galaxy. Still, it's important not to exaggerate the difference. These are not galaxies of entirely different classes. Andromeda is not a giant dwarfing a much smaller Milky Way. They are peers. If galaxies could be described as siblings, these two would be close in stature. Structure provides another point of comparison. Andromeda's spiral arms are more clearly defined in images. This clarity comes partly from our external perspective, and partly from genuine differences in star formation patterns. Andromeda's disk shows prominent dust lanes and a well-defined central bulge. The Milky Way also has spiral arms and a central bulge, but their exact number and shape are still subjects of study. From within, the view is obscured by dust and overlapping structures. This makes the Milky Way feel less orderly in comparison, though that impression may be misleading. Central regions differ as well. Both galaxies host supermassive black holes at their centres. Andromeda's central black hole appears to be more massive than the Milky Way's, though again, the difference is not extreme. These black holes influence the dynamics of their immediate surroundings, but do not dominate the galaxy as a whole. Star populations offer further contrast. Andromeda contains a larger proportion of older stars compared to the Milky Way, suggesting differences in star formation history. This does not directly affect size, but it influences how light is distributed and how the galaxy appears. The Milky Way, meanwhile, continues to form new stars at a steady rate, fueled by gas within its disk. Andromeda's star formation has slowed somewhat, particularly in its outer regions. This difference affects brightness patterns, but not necessarily spatial extent. Satellite galaxies also contribute to perceived size. Both Andromeda and the Milky Way are surrounded by dozens of smaller galaxies orbiting them. Andromeda's satellite system appears more extensive and more massive overall. These satellites trace the gravitational reach of the main galaxy, extending its influence farther into space. Some of Andromeda's satellites are themselves sizable dwarf galaxies containing billions of stars. Their orbits stretch far out, marking the outer limits of Andromeda's gravitational domain. The Milky Way's satellites perform a similar role, though their distribution may be somewhat less expansive. These satellite systems are not static. Over time, small galaxies are drawn inward, stretched, and sometimes absorbed. The remnants of these mergers appear as stellar streams, which, in Andromeda's case, are particularly prominent. These streams extend far beyond the main disk, adding to the galaxy's effective size. The Milky Way has its own stellar streams, evidence of past mergers. From inside, they are harder to map fully, but they exist nonetheless. Their presence suggests that both galaxies have grown over time through similar processes, gradually expanding their reach. Another subtle difference lies in orientation. Andromeda is tilted relative to our line of sight, allowing us to see its disk at an angle. This makes its structure easier to interpret visually. The Milky Way's disk, by contrast, surrounds us. Its scale is felt rather than seen. This difference in perspective can distort comparison. Something seen from the outside often appears more coherent and larger than something experienced from within. Imagine comparing two cities, one viewed from a satellite image and the other navigated street by street. The satellite view gives immediate scale. The street-level view emphasizes detail but obscures overall size. Emotionally, Andromeda often feels larger because it is visible as a whole. The Milky Way feels abstract because we cannot step back and look at it. This psychological factor is worth acknowledging. It shapes how size is perceived even when measurements suggest similarity. Another aspect of comparison involves motion. Andromeda's rotation speed, the way stars orbit its centre, provides clues to its mass distribution. These speeds are comparable to those in the Milky Way, reinforcing the idea that their internal dynamics are alike. Despite these similarities, Andromeda's extended outer regions appear richer in structure. More stellar streams have been identified. More substructure has been mapped. This could reflect genuine differences, or it could simply reflect observational bias. Andromeda is easier to study in this way. As research continues, the gap between what we know about Andromeda and what we know about the Milky Way gradually narrows. New surveys map our galaxy's halo and streams with increasing precision. As that happens, the comparison becomes more balanced. For now, it is fair to say that Andromeda is slightly larger and more massive than the Milky Way, but not overwhelmingly so. They occupy similar volumes of space. Their halos may already overlap at the edges. Their future interaction will blend these distinctions entirely. Thinking about them together highlights an important point about galactic size. Size is not just a number, it is a relationship. It depends on environment, history, and perspective. Andromeda's size only becomes meaningful when set beside something like the Milky Way. This comparison also grounds Andromeda's scale in something personal. The Milky Way contains everything familiar. Knowing that Andromeda is comparable in size means imagining another structure capable of holding hundreds of billions of stars, countless planets, and potentially its own forms of complexity. There is no need to rush this realization. It does not need to arrive as awe or astonishment. It can settle quietly as a steady understanding that the universe repeats patterns on scales far larger than individual experience. As the comparison lingers, the next thought follows naturally. If both galaxies are so large, and if their outer regions extend so far, what lies between them? How do their invisible components interact long before their visible disks approach? Beyond the bright spiral arms and the familiar oval glow that images usually show, Andromeda continues. Not visibly, not in a way that announces itself, but in a way that fundamentally changes how large the galaxy truly is. This continuation is quiet, extended, and easy to overlook. Yet it accounts for a significant portion of Andromeda's size and almost all of its gravitational authority. This region is known as the halo, and without it, Andromeda would be a very different galaxy. The word halo can be misleading if taken too literally. It does not describe a thin ring or a glowing outline. Instead, it refers to an enormous, roughly spherical volume surrounding the galaxy, extending far beyond the bright disk. Within this volume are stars, gas, and a much larger amount of dark matter, all bound together by gravity. The halo is not decorative, it is structural. When astronomers first began to suspect the existence of galactic halos, it was not because they saw them directly. It was because galaxies did not behave the way they should if only their visible matter were present. Stars in the outer regions of galaxies moved too fast. Gas clouds followed unexpected paths. The gravitational pull required to explain these motions exceeded what could be accounted for by stars and gas alone. In Andromeda, this discrepancy was especially clear. Measurements of how stars orbit the galaxy showed that the mass continued to increase far beyond the visible edge. If all the mass were concentrated in the bright disk, orbital speeds should drop with distance, the way planets slow down the farther they are from the Sun. Instead, the speeds remained high, implying that mass was spread out over a much larger region. This unseen mass is what we call dark matter. It does not emit light. It does not block light. It does not interact with ordinary matter in ways we can easily detect. Yet its gravitational influence is undeniable. In Andromeda, dark matter forms a vast halo that envelops the entire galaxy and extends far into surrounding space. The size of this dark matter halo dwarfs the visible galaxy. While the bright disk of Andromeda spans roughly 200,000 light-years, The dark matter halo may extend close to 1,000,000 light-years across. That means the galaxy's true footprint in space is several times larger than what images suggest. This halo is not empty of ordinary matter. Scattered within it are stars, many of them ancient, dim and widely spaced. These stars are remnants of Andromeda's long history. Some formed early in the galaxy's life. Others were pulled in from smaller galaxies that merged with Andromeda over billions of years. These mergers leave traces. Long, faint streams of stars arc through the halo, marking the paths of disrupted galaxies. Each stream tells a story of interaction, of gravity reshaping smaller systems and folding them into a larger one. Together, these streams expand the effective size of Andromeda even further. Detecting these halo stars requires patience. They are too faint to see individually without long observations. Large surveys and sensitive detectors are needed to map them. When these maps are assembled, the halo emerges not as a smooth sphere, but as a textured, complex structure filled with substreams and clumps. Gas also occupies the halo, though in forms that are difficult to detect. Some of this gas is cool and neutral. Some is hot and ionized, interacting with the broader environment of the local group. This gaseous component plays a role in future star formation, serving as a reservoir that can slowly feed the galaxy over time. The halo's role extends beyond size alone. It stabilizes the galaxy. The distribution of dark matter helps maintain the spiral structure by influencing how stars and gas move. Without the halo, the visible disk might not hold together in its current form. This makes the halo central to Andromeda's identity. The bright disk is what we notice. The halo is what makes that disk possible. In this sense, much of Andromeda's true substance lies in a region we cannot see directly. From Earth, the halo is completely invisible to the naked eye. Even many telescopes cannot detect it without specialized techniques. Its presence is inferred rather than observed in the traditional sense, yet its effects are measurable, repeatable, and consistent. This invisibility challenges intuition. We tend to associate size with visibility. Larger things are easier to see. In the universe, this is often not the case. The largest components can be the most elusive. Andromeda's halo contains far more mass than its stars, yet contributes almost nothing to its brightness. The idea that most of a galaxy's size and mass are hidden can feel unsettling at first. It suggests that what we see is only a surface layer, a luminous skin over a much deeper structure. But this idea also brings coherence. It explains why galaxies behave as they do. It provides a framework that unifies observations across many systems, not just Andromeda. The halo also defines Andromeda's sphere of influence. Objects within the halo are gravitationally bound to the galaxy. They move in response to its mass. Beyond the halo, gravity from other galaxies and the expansion of the universe become more important. In this way, the halo marks the galaxy's effective boundary. This boundary is not fixed. Over time, halos grow as galaxies accumulate more matter. They can also be reshaped by interactions with neighbouring galaxies. In Andromeda's case, its halo already overlaps slightly with that of the Milky Way. This overlap does not mean the galaxies are colliding yet, but it does mean their gravitational environments are interacting. This interaction begins long before any visible contact. The halos feel each other's presence across hundreds of thousands of light years. Subtle effects ripple through their outer regions, altering the paths of stars and gas. The future merger of Andromeda and the Milky Way is already underway in this invisible sense. Understanding the halo reframes the idea of galactic size. Andromeda is not just the bright spiral you might picture. It is a massive, extended structure whose true dimensions are defined by gravity rather than light. Its size is measured not only in how far its stars reach, but in how far its influence extends. This influence matters for smaller galaxies nearby. Many of Andromeda's satellite galaxies orbit within its halo. Their paths, shapes, and eventual fates are governed by the halo's mass. Some are gradually being pulled apart. Others remain intact but altered. The halo also interacts with the broader environment of the local group. Gas flows between galaxies. Dark matter halos interpenetrate. The local group itself is a collection of overlapping halos rather than a set of isolated disks floating in empty space. From this perspective, galaxies are less like islands and more like weather systems, extended, overlapping, and dynamic. Their boundaries blur. Their interactions are subtle and long-lasting. Size becomes a matter of degree rather than a line drawn in space. Thinking about Andromeda's halo can also change how one thinks about emptiness. The space around galaxies is not vacant. It is filled with structure that simply does not announce itself visually. Darkness often signals not absence, but limitation of perception. This realization carries forward naturally. If much of Andromeda's size lies in what we cannot see, then understanding its full scale requires thinking beyond images. It requires trusting indirect evidence, patterns of motion, and long-term behavior. As the idea of the halo settles in, it becomes clear that any discussion of Andromeda's size that ignores it is incomplete. The halo is not an add-on. It is the dominant component. It turns a large galaxy into a truly enormous one. Inside Andromeda, size does not announce itself through crowding or density, but through separation. The galaxy is enormous, not because everything is packed tightly together, but because so much space exists between the things that shine. Stars, dust, and gas occupy only a small fraction of the volume, yet they define the structure, motion, and long-term evolution of the whole system. Understanding how much emptiness exists between these components is essential to understanding what Andromeda really is. A galaxy is often imagined as a swirling mass of stars brushing past one another, a luminous city in constant motion. This picture is understandable, but it is misleading. In reality, stars in Andromeda are separated by distances so large that collisions are extraordinarily rare. Even in the densest regions, stars are spaced light years apart. In the outskirts, that spacing increases dramatically. To put this into perspective, imagine shrinking Andromeda down so that each star were the size of a grain of sand. Even then, the grains would be separated by distances comparable to kilometers. The galaxy would still be mostly empty space. This emptiness is not a flaw in the system. It is what allows galaxies to exist without tearing themselves apart. Stars form within clouds of gas and dust, but once they ignite, they spend most of their lives isolated. They orbit the galactic center along paths shaped by gravity, rarely interacting directly with other stars. Their influence on one another is subtle, mediated through the collective gravitational field rather than close encounters. In Andromeda, this structure is repeated hundreds of billions of times. Each star follows its own trajectory, bound to the galaxy as a whole rather than to its immediate neighbours. The result is a system that is vast, stable, and remarkably orderly when viewed over long periods. Dust adds another layer of complexity. Galactic dust is not like household dust. It consists of tiny solid particles, often smaller than smoke grains, made of carbon, silicon, ice, and other elements. These particles drift through space mixed with gas, forming clouds that can stretch for hundreds of light years. In Andromeda's spiral arms, dust is especially prominent. Dark lanes cut across the glowing disk, blocking light from stars behind them. These lanes are not gaps where nothing exists. They are regions where dust is dense enough to absorb and scatter light. The dust itself occupies very little mass compared to stars, but it plays an outsized role in shaping what we see. Dust marks sites of future change. Within these clouds, gas can cool and collapse, eventually forming new stars. In this sense, dust is not debris. It is raw material. It connects past generations of stars to future ones, recycling elements forged in stellar interiors. Despite its importance, dust occupies only a tiny fraction of Andromeda's volume. Most of the space between stars contains gas so thin that it would be considered a vacuum by terrestrial standards. Even the densest interstellar clouds are emptier than any laboratory vacuum on Earth. This vast emptiness is what allows light to travel freely across the galaxy. Photons can move for thousands of years without encountering anything substantial. When we see Andromeda's light, it has passed through enormous regions of near-nothingness, interacting only occasionally with dust or gas. The emptiness also allows stars to orbit smoothly. Without frequent collisions or drag, stars maintain stable paths for billions of years. This stability gives Andromeda its enduring structure. Spiral arms persist. The disk remains coherent. Change happens slowly. From a human perspective, emptiness often implies absence or insignificance. In a galactic context, emptiness is functional. It is the medium that makes large-scale organization possible. If Andromeda were densely packed, it would be chaotic. Stars would collide. Orbits would be unstable. The galaxy would evolve violently. Instead, Andromeda evolves gently. Stars are born, age, and die, largely undisturbed by their neighbours. Supernovae inject energy into surrounding gas, but even these dramatic events affect only limited regions. On the scale of the galaxy, they are local ripples. The balance between matter and emptiness is what defines Andromeda's scale. The galaxy stretches across hundreds of thousands of light years, not because it is filled throughout, but because its components are spread thinly across that space. Size emerges from distribution, not density. In the central regions where stars are more closely packed, the feeling of scale shifts slightly. The core of Andromeda contains a higher concentration of stars. Orbits are tighter. Gravitational interactions are stronger. Even here, though, the distances between stars remain vast. Moving outward into the disk, spacing increases. Spiral arms appear as patterns not because stars are physically linked, but because their orbits align in waves of higher density. These waves pass through the disk, compressing gas and triggering star formation as they go. Between the arms, stars still exist. The space is not empty of stars, only less crowded. Light from these regions contributes to the galaxy's glow, even if it is fainter. Again, the emptiness is relative. Beyond the disk in the halo, emptiness dominates even more. Stars are few and far between. Gas is extremely thin. Yet this region occupies a huge volume. It is here that the scale of Andromeda truly asserts itself. If one were hypothetically travelling through Andromeda, the journey would be defined by long stretches of nothing punctuated by rare encounters with stars or clouds. There would be no sense of passing through a crowded environment. The galaxy would feel spacious almost to the point of monotony. This thought experiment highlights a key point. Galaxies are not places in the way planets are places. They are frameworks. They provide gravitational context rather than physical environments. Most of their volume is unoccupied in any meaningful sense. The vast empty spaces between stars also explain why galaxies can overlap without immediate destruction. When Andromeda and the Milky Way eventually merge, their stars will not crash into one another en masse. Instead, they will pass by, their orbits gradually reshaped by changing gravitational fields. The merger will be slow and subtle on a local scale, even if dramatic in overall structure. The emptiness allows for this gentleness. Without it, galactic interactions would be violent beyond recognition. Dust clouds will interact more directly. Gas will compress, triggering bursts of star formation. Yet even these processes unfold over millions of years. Emptiness stretches time as well as space. This connection between emptiness and duration is important. Because matter is sparse, change is slow. Because change is slow, structures persist. Andromeda's size is maintained not just spatially, but temporally. The galaxy has had billions of years to spread out to settle into equilibrium. Stars drift outward and inward, gas cycles through phases, dust forms and disperses. All of this happens within a framework that is mostly empty, allowing gradual evolution rather than constant disruption. When images of Andromeda are shown, the emptiness is often hidden. Bright stars and glowing gas dominate the frame. Dark regions are sometimes filled in or ignored. This visual emphasis can create the impression of a crowded system. In reality, those images are maps of highlights, not of volume. They show where light is concentrated, not where space is abundant. The true structure is revealed not by brightness alone, but by understanding what lies between the bright regions. That understanding requires letting go of the idea that emptiness is uninteresting. In astronomy, emptiness is often the main story. It defines scale. It allows motion. It preserves structure. The emptiness inside Andromeda also mirrors the emptiness between galaxies. On every scale, from stellar neighborhoods to galactic clusters, space dominates matter. This repetition suggests a fundamental pattern in how the universe organizes itself. Matter gathers where conditions allow, but it never fills space completely. Gravity shapes distributions, but it does not eliminate gaps. The result is a universe that is structured yet sparse, ordered yet open. For someone listening quietly, letting this idea settle can be unexpectedly calming. The universe is not crowded. It is not pressing in. Even its largest structures are mostly space. There is room everywhere. This sense of room extends inward as well. The stars that make up Andromeda are not competing for space. They coexist across enormous distances, each following its path without interference. The galaxy's size allows for this coexistence. Dust, though visually striking in images, occupies little volume. Gas, though essential, is diffuse. Stars, though numerous, are isolated. Together they form a system that is defined as much by what is absent as by what is present. As attention drifts from components to the spaces between them, the idea of scale becomes less overwhelming. Size no longer means crowding or compression. It means reach, separation, and patience. Gravity is easy to underestimate because it feels so gentle here. You can jump and you come back down. You can lift an object and it resists slightly. On human scales, gravity is familiar, predictable, almost background noise. Nothing about it suggests that it could be responsible for holding together something as vast as the Andromeda galaxy. And yet, gravity is the only reason Andromeda exists as a coherent structure at all. At the scale of a galaxy, gravity stops being a subtle force and becomes an organizing principle. It does not act through sudden pulls or dramatic tugs. Instead, it works patiently, continuously, across enormous distances, binding together stars that will never come close to one another, gas clouds that drift for millions of years, and invisible matter that never emits light. Without gravity, Andromeda would not be a galaxy. It would be a loose scattering of material, slowly dispersing into intergalactic space. The first thing to understand is that gravity does not require closeness to be effective. It weakens with distance, but it never truly turns off. Even across hundreds of thousands of light years, the combined gravitational pull of Andromeda's mass is enough to guide the motion of stars and gas. Individual stars may feel only a tiny pull from any one neighbour, but they feel the collective pull of the entire galaxy. This collective effect is crucial. No star in Andromeda orbits another star in the way planets orbit the Sun. Instead, each star orbits the galaxy's centre of mass, responding to the overall gravitational field generated by everything else. That field is smooth on large scales, even though it is built from countless individual contributions. Because Andromeda is so large, gravity acts differently than it does in smaller systems. In a solar system, gravity is dominated by one massive object, the star. In a galaxy, there is no single dominant source in the same way. The mass is spread out. The central region contributes strongly, but so do the disk, the halo, and especially the dark matter component. This distributed mass creates a gravitational environment that is stable over very long timescales. Stars follow predictable orbits that change only slowly. Gas clouds drift, collide, and collapse, but always within the constraints imposed by the galaxy's gravity. Nothing is free to simply wander off unless it gains enough energy to escape the galaxy's pull. Escape is not easy. To leave Andromeda entirely, a star or gas cloud would need to reach a speed high enough to overcome the gravitational influence of the entire galaxy, including its dark matter halo. Such speeds are rare. They can occur in extreme events, like close encounters with other galaxies or interactions near the galactic center, but they are exceptions rather than the rule. For most of Andromeda's material, gravity acts like a deep, wide basin. Objects move within it, but climbing out requires an extraordinary push. This basin is not visible, but it defines the galaxy's true shape and extent. One way astronomers understand this basin is by studying how fast stars orbit at different distances from the center. In Andromeda, stars far from the center move faster than expected if only visible matter were present. This observation tells us that gravity is stronger there than light alone would suggest. The extra pull comes from dark matter, distributed throughout the halo. Dark matter's role in holding Andromeda together cannot be overstated. It provides most of the mass. It deepens the gravitational basin. It stabilizes the rotating disk. Without it, Andromeda's stars would not orbit as they do. The galaxy might not even remain intact over billions of years. This stabilization is subtle. Gravity does not clamp stars into rigid positions. It allows motion. In fact, motion is essential. The rotating disk of Andromeda exists because stars and gas are moving fast enough sideways to avoid falling straight into the center, yet not fast enough to escape entirely. This balance between inward pull and sideways motion is what creates stable orbits. In Andromeda's disk, stars follow roughly circular paths around the center. These paths are not perfect circles, but they are stable enough that the disk maintains its overall shape. Spiral arms emerge not because stars are fixed in place, but because gravity organizes motion into patterns of higher density. These patterns are another example of gravity working on large scales. Spiral arms are not permanent structures made of the same stars. They are waves of density that move through the disk, compressing gas and triggering star formation as they go. Gravity sets the conditions for these waves to exist and persist. In the central regions, gravity becomes stronger. Stars orbit more quickly. The gravitational field is influenced by the dense concentration of stars and by the presence of a supermassive black hole. Even here, gravity does not dominate through violence. Stars do not fall straight in. They continue to orbit, constrained by angular momentum and by the distribution of mass around them. The black hole at Andromeda's center is massive, but its influence is limited to a relatively small region compared to the galaxy as a whole. It does not hold the galaxy together. It is a detail within a much larger gravitational structure. Farther out in the halo, gravity's role shifts again. Here, stars are sparse and orbits are more elongated. Some stars travel on paths that take them far above and below the disk. Others follow streams left behind by disrupted satellite galaxies. Gravity governs all of these motions, even though the stars themselves may be separated by enormous distances. These halo stars move slowly, completing orbits that take hundreds of millions or even billions of years. Their motion traces the shape of the galaxy's gravitational field, offering clues to its total mass and extent. By mapping these motions, astronomers can infer how far Andromeda's influence reaches. Gravity also acts on gas beyond the visible disk. Hot, diffuse gas in the halo is held in place by the galaxy's mass. This gas does not collapse easily. It drifts, cools, and occasionally falls inward, contributing to future star formation. Without gravity, it would simply disperse into intergalactic space. On even larger scales, gravity ties Andromeda to its surroundings. Satellite galaxies orbit within its halo, bound by its mass. Their paths are shaped by Andromeda's gravity, and over time many are drawn inward, stretched and absorbed. Each merger adds mass and extends the galaxy's reach. This process of growth is slow and steady. Gravity does not rush, it accumulates. Over billions of years, small changes add up. Andromeda today is larger than it was in the past, not because it expanded suddenly, but because gravity gradually incorporated more material. The same gravity that holds Andromeda together also connects it to the Milky Way. The two galaxies are falling toward each other under mutual attraction. This motion is gentle. It unfolds over millions of years. Yet it is inexorable. Gravity does not forget. Once objects are bound, they remain bound unless acted upon by something stronger. At this scale, gravity shapes not just individual galaxies, but the structure of the universe itself. Galaxies gather into groups. Groups gather into clusters. Clusters form vast filaments separated by immense voids. Andromeda's place within this structure is defined by gravity acting over hundreds of millions of light years. Understanding gravity at galactic scales requires letting go of the idea that it is a force you feel directly. No human has felt Andromeda's gravity in any noticeable way. Its pull on you is utterly negligible. Yet its pull on stars and gas across its own vast extent is decisive. This mismatch between personal experience and cosmic effect is one reason gravity feels abstract in astronomy. It does not announce itself. It reveals itself through motion, through patterns, through stability over time. It must be inferred rather than felt. The fact that gravity can hold something as enormous as Andromeda together does not mean it is rigid. The galaxy is not frozen. Stars drift, orbits precess, structures evolve. Gravity provides cohesion, not stasis. It allows change without disintegration. This balance is delicate. If Andromeda's stars moved too slowly, gravity would pull them inward, collapsing the galaxy. If they moved too quickly, they would escape, dispersing the system. The fact that neither happens reflects a long history of gradual adjustment. That adjustment began when Andromeda first formed, from fluctuations in the early universe. Gravity amplified tiny differences in density, pulling matter together. Over time, those clumps grew, merged, and settled into the rotating disk and halo we see today. Even now, gravity continues to work. It shapes the orbits of newly formed stars. It guides the motion of gas clouds. It governs interactions with neighbouring galaxies. Nothing in Andromeda is exempt from its influence. Yet gravity does all of this without effort, without exhaustion, without direction. It does not plan. It does not choose. It simply acts according to the distribution of mass and energy. The order we see emerges naturally from that simplicity applied over immense scales and long durations. For someone listening quietly, this can be a reassuring thought. Something so large, so complex, is held together by the same basic principle that keeps your feet on the ground. The difference is not in the nature of gravity, but in the scale at which it operates. Andromeda's enormity does not overwhelm gravity. Gravity thrives on scale. The more mass there is, the stronger the collective pull becomes. Size, in this sense, reinforces cohesion rather than threatening it. It becomes easier to see Andromeda not as a fragile arrangement of distant lights, but as a stable, long-lived system. Its size is not a liability. It is a consequence of gravity having enough material and enough time to work with. If gravity holds Andromeda together now, what does that mean for its future? How does a system this large change when guided by such a patient force? Long before any visible signs appear in the sky, long before stars seem to shift or patterns look unfamiliar, a gradual interaction has already begun. It does not announce itself with motion you can see, or changes you can measure in a lifetime. It unfolds so slowly that even calling it an event feels misleading. Yet this process is real, ongoing, and inevitable. Andromeda and the Milky Way are engaged in a slow gravitational dance, one that has been developing for billions of years and will continue long after the present moment fades. This dance does not resemble the kind of movement we associate with collision or impact. There is no rushing toward a crash, no dramatic spiral inward that can be watched unfolding. Instead, it is more like two enormous systems responding to each other's presence, adjusting their paths subtly under the influence of gravity. Their motion is gentle, patient, and governed by forces that operate on scales far beyond human intuition. At present, Andromeda and the Milky Way are separated by a little over 2 million light-years. That distance is immense, yet in cosmic terms it is small. Both galaxies belong to the same local group, a loose collection of galaxies bound together by gravity. Within this group, Andromeda and the Milky Way dominate. Their combined mass shapes the motion of everything around them. Measurements show that Andromeda is moving toward us. Its light is slightly blue-shifted, meaning its wavelengths are compressed, a sign that the distance between us is decreasing. This approach is not fast by everyday standards, but it is steady. Hundreds of kilometers per second sounds dramatic until it is spread across millions of years. On that timescale, the movement becomes almost imperceptible. The Milky Way is not standing still either. It moves in response to Andromeda's pull, and both galaxies move through the gravitational landscape of the local group. Their paths are not straight lines through empty space. They are curves shaped by mass, influenced by the presence of smaller galaxies, dark matter halos, and the expanding universe itself. The idea of a dance is useful because it emphasizes relationship rather than destination. Andromeda and the Milky Way are not simply heading for a collision point. They are orbiting a shared center of mass, adjusting their motion continuously. Their interaction began long before they were as close as they are now, and it will continue long after their visible structures begin to overlap. Even now, long before any stars come close to one another, the outer regions of both galaxies are interacting. Their dark matter halos extend far beyond their visible disks. These halos are already brushing against each other, overlapping slightly in the vast space between the galaxies. This overlap marks the true beginning of their merger. In this overlapping region, gravity from each galaxy influences the other's outermost stars and gas. The effects are subtle. Orbits are gently perturbed. Paths are slightly altered. Nothing dramatic happens quickly. Yet over millions of years, these small changes accumulate. This is how gravity works on large scales. It rarely produces sudden transformations. Instead, it nudges systems toward new configurations slowly, allowing structures to adjust without breaking apart. The dance between Andromeda and the Milky Way follows this pattern precisely. As the galaxies draw closer, their relative motion will change. They will not collide head-on. Instead, they are expected to pass by one another at a distance, pulled into elongated orbits by their mutual attraction. This first close passage will stretch both galaxies, drawing out long tidal tails of stars and gas. These tidal features are common in interacting galaxies observed elsewhere in the universe. They are evidence of gravity redistributing material without destroying it outright. In the case of Andromeda and the Milky Way, such features will develop slowly, over hundreds of millions of years. During this time, the night sky from Earth, if Earth still exists, would change gradually. New stars would appear. Familiar constellations would distort. Yet even these changes would be subtle on human timescales. No single generation would witness dramatic transformation. After the first close pass, the galaxies will move apart again, but not enough to escape each other's pull. Gravity will draw them back together for another pass, and then another. Each encounter will drain orbital energy, allowing the galaxies to settle into a closer configuration. This back-and-forth motion is characteristic of galactic mergers. They are not single events, but extended processes. The term collision is misleading. Stars do not slam into one another. The emptiness within galaxies ensures that direct stellar collisions remain extremely rare. Instead, what changes is the overall structure. Disks are distorted, spiral patterns are disrupted, gas clouds compress, triggering bursts of star formation. Over time, the distinct identities of the original galaxies begin to blur. Eventually, after several such passages, Andromeda and the Milky Way will merge into a single, larger galaxy. This new system will likely have a different shape, possibly more elliptical than spiral. Its size will exceed that of either original galaxy, its halo expanding to encompass the combined mass. Throughout this process, gravity remains the guiding force. It orchestrates the motion, redistributes material, and allows the system to relax into a new equilibrium. Nothing happens without gravity's quiet involvement. From a distance, such mergers appear dramatic in telescope images. Long streams of stars stretch across space. Bright regions flare where gas is compressed. Yet these images capture moments in a process that spans billions of years. They freeze what is otherwise a slow unfolding. For someone living within one of the merging galaxies, the experience would be far less dramatic. The sky would change gradually. Star formation would increase in some regions. Over long periods, the distribution of stars would shift. There would be no sudden catastrophe. This gentle nature is a direct consequence of scale. The larger the system, the slower the change. Andromeda's size ensures that its interaction with the Milky Way is drawn out, giving matter time to respond without violent disruption. The dance also involves the galaxy's satellite systems. Smaller galaxies orbiting Andromeda or the Milky Way will have their paths altered. Some will be captured by the combined system. Others may be flung outward, escaping into intergalactic space. These satellites act like tracers, revealing the structure of the gravitational field. Their motions provide clues about their mass distribution of the interacting galaxies. As the merger progresses, these motions become more complex, reflecting the evolving shape of the combined halo. Dark matter plays a crucial role here as well. The dark matter halos of both galaxies merge long before the visible components do. This merger deepens the gravitational potential, guiding the motion of stars and gas during later stages. Because dark matter dominates the mass budget, it largely determines the outcome. The visible stars respond to a gravitational landscape shaped primarily by something they cannot interact with directly. This separation between what shines and what guides motion is a defining feature of galactic dynamics. The slow dance between Andromeda and the Milky Way is not unique. Similar interactions have occurred countless times throughout the universe. Galaxies grow by merging. Large galaxies today are the result of many such dances, layered one upon another over cosmic time. This context helps normalize the future interaction. It is not an anomaly. It is part of a broader pattern. Andromeda and the Milky Way are following the same evolutionary path that countless other galaxies have followed before. From this perspective, the dance is not something to fear or dramatize. It is simply how structure evolves in the universe. Gravity brings matter together. Systems interact. New systems emerge. The timescales involve dwarf human concerns. The first close encounter is expected to occur billions of years from now. By then, the Sun will be nearing the end of its life. Earth's environment will be profoundly different, if the planet still exists at all. This temporal distance can make the dance feel abstract. Yet it is happening now, in the sense that the initial conditions are already in place. The galaxies are already moving toward each other. The gravitational relationship already exists. Understanding this relationship also sheds light on Andromeda's size. Its extended halo is what allows the interaction to begin so early. If galaxies were defined only by their bright disks, they would remain isolated until much closer. The halo expands the reach of gravity, allowing interactions across vast distances. This expanded reach means that Andromeda's size is not just a matter of physical extent, but of influence over time. Its gravitational pull shapes not only its own structure, but the future of the local group as a whole. As Andromeda and the Milky Way continue their dance, the local group itself may change. Smaller galaxies may be absorbed. The group may become more tightly bound. Over even longer timescales, interactions with other nearby groups could occur. All of this unfolds within the broader expansion of the universe. On very large scales, Space itself is stretching, carrying distant galaxies away from each other. On smaller scales, gravity counters this expansion, binding systems together. The dance between Andromeda and the Milky Way exists at this boundary between expansion and attraction. This balance highlights a deeper point. Size in the universe is meaningful only in relation to other sizes and forces. Andromeda's size matters because it is large enough for gravity to overcome expansion locally. Smaller systems cannot do this. Larger clusters can. The slow dance is therefore a consequence of Andromeda's scale. It has enough mass, spread across enough space, to influence its surroundings decisively. That influence extends far beyond its visible stars, reaching across the darkness between galaxies. For someone listening quietly, this idea can be grounding. The universe is not a place of sudden chaos. Even its largest transformations are measured and patient. Change happens, but it happens slowly. As attention lingers on this future interaction, another question naturally arises. If Andromeda and the Milky Way are destined to merge, what will the combined system be like? How large will it become? How will its structure compare to what exists now? Imagine stepping outside on a clear night and sensing that something about the sky feels different before you consciously register why. The familiar patterns are still there, but they seem pushed aside, as if the background itself has changed. There is a broad, luminous presence stretching across the darkness, not sharp or blinding, but impossible to ignore. This is not a star or a planet. It is not the moon. It is Andromeda, close enough now that its true size finally reveals itself to human eyes. If Andromeda filled our sky, the first surprise would be that it would not feel overwhelming in the way people often imagine. There would be no sudden blaze of light turning night into day. Galaxies are vast, but their light is spread thinly across enormous areas. Instead of brilliance, there would be breadth. A soft, continuous glow would arc across the sky, stretching far beyond the span of any constellation. The central region would appear as a brighter oval, large enough to cover a significant fraction of the sky on its own. It would not have a hard edge. The brightness would fade gradually outward, blending into fainter extensions that would be visible only under dark conditions. The transition from galaxy to sky would be subtle, requiring attention to notice where one ended and the other began. From horizon to horizon, Andromeda's disk would dominate the view. Its spiral structure would be visible not as crisp arms like those seen in photographs, but as broad variations in brightness. Dark lanes of dust would cut through the glow, forming irregular patterns that would shift slightly as the Earth rotated beneath them. These lanes would be striking because they would block light rather than emit it, creating contrast within the galaxy's own glow. The Milky Way, as we know it, would still exist, but it would feel secondary. Its familiar band of light would cross Andromeda's glow, the two galaxies overlapping visually while remaining distinct in structure. The sky would become layered, a tapestry of galactic light woven together rather than a backdrop punctuated by stars. Individual stars would still be visible, scattered across the foreground. Some would shine against Andromeda's glow, appearing sharper by contrast. Others would be harder to pick out, lost in the diffuse light behind them. Constellations would be difficult to recognize. Their patterns depend on dark space between stars, and that darkness would be partially filled. The moon, when present, would carve out a bright path through Andromeda's light. Its movement across the sky would temporarily erase parts of the galaxy from view, only for them to reappear as the moon passed on. This interaction would make the scale of Andromeda more apparent. The moon would seem small by comparison, a moving object crossing an immense stationary background. On moonless nights, the effect would be more pronounced. Andromeda's outer regions would be visible only under the darkest skies, appearing as faint extensions that reached far beyond the bright core. The galaxy would not end abruptly. It would thin gradually, its light fading into the general darkness. The sense of depth would be subtle but persistent, Unlike clouds or atmospheric effects, Andromeda would not shift or change shape from night to night. Its presence would be stable, reinforcing the impression that this glow was not part of Earth's environment, but something far beyond it. Seasonal changes would alter how Andromeda appeared in the sky. As Earth orbited the Sun, the angle at which we viewed the galaxy would change slightly. Different parts would be higher or lower at different times of year. The galaxy would rise and set, its enormous structure slowly moving across the sky over the course of hours. This motion would be gentle. There would be no sense of Andromeda sweeping overhead. Instead, it would drift with the rotation of the Earth, reinforcing the idea that it is part of the sky itself, rather than an object within it. Photographs taken under such conditions would struggle to capture the full effect. Cameras are good at recording detail, but they often compress dynamic range. The experience of seeing Andromeda fill the sky would rely on peripheral vision, on subtle gradients of light, on the mind's ability to integrate faint signals across a wide field. The emotional response to such a sky would likely be complex. Awe would be present, but not in a sharp or startling way. Instead, there would be a sense of scale that settles in slowly. The galaxy's size would not confront you all at once. It would reveal itself over time, as you noticed how much of the sky it occupied. Navigation by the stars would become more difficult. Traditional reference points would be obscured or altered by Andromeda's glow. New patterns would emerge instead, based on the galaxy's structure. People would learn to recognize regions of Andromeda the way they now recognize constellations. The idea of darkness would change. Night would no longer mean a mostly black sky punctuated by points of light. It would mean a luminous sky with darker features embedded within it. True darkness would be rarer, confined to regions where the galaxy's light was weakest. Despite this, the sky would not feel crowded. Andromeda's light is diffuse. It would not press down or feel heavy. The emptiness between stars would still be vast. The glow would be more like a background illumination than a ceiling. The presence of Andromeda would also change how distance feels. With such a massive structure visible, the idea of the universe as something far away would soften. The galaxy would feel like part of the local environment, even though it remained millions of light years distant. This closeness would be deceptive. The galaxy would look near, but it would still be unreachable. The light filling the sky would still be ancient. Knowing this would add a quiet tension to the experience, a reminder that appearance does not equal proximity. Cultural responses would evolve around such a sky. Stories, myths, and calendars would incorporate Andromeda's presence. Its structure would become a reference for time and direction. The galaxy would serve as a constant reminder of something larger than any planet or star. Science would also adapt. Observing other galaxies would become more challenging, as Andromeda's glow would interfere with faint observations. Astronomers would develop new techniques to filter out its light, treating it as background rather than subject. The psychological effect of living under such a sky is difficult to predict. Some might find it comforting, a constant luminous presence overhead. Others might find it unsettling, a reminder of scale that is hard to ignore. Over generations, it would become normal, woven into daily life. The sense of rarity that now accompanies seeing Andromeda would disappear. No longer would it be a faint smudge sought out on dark nights. It would always be there, impossible to miss. Its familiarity might dull its impact, even as its size remained unchanged. This familiarity would not make Andromeda smaller. It would make our perception adjust. What feels extraordinary at first often becomes background with time. The galaxy would still be vast, our response to it would simply evolve. The idea of Andromeda filling the sky also highlights how much of scale is perceptual. The galaxy is already enormous. The only thing that changes in this scenario is distance. By imagining it closer, we allow our senses to engage with its size directly rather than through numbers. This exercise reveals why size is so difficult to grasp in astronomy. Distance hides scale. When distance is removed, scale becomes immediately apparent. not through calculation, but through experience. Yet even in this imagined closeness, Andromeda would not feel solid or imposing. It would feel expansive and calm. Its light would be gentle, its structure would unfold slowly across the sky, inviting observation without demanding it. As the night progressed and as attention drifted, Andromeda's presence would likely fade into awareness rather than dominate it. The mind adapts. What is constant becomes context rather than focus. This imagined sky also reinforces an earlier idea. Galaxies are mostly empty. Even when one fills the sky, most of what you're seeing is space, lightly traced by stars and dust. The glow is thin, the emptiness remains. Thinking about Andromeda in this way prepares the mind for another shift. If seeing the galaxy close makes its size intuitive, then travelling across it introduces a new challenge. Distance within the galaxy becomes the next scale to consider. The question naturally follows, if Andromeda filled our sky, how long would it take to cross it? What does size mean when measured not in appearance but in time and travel? Suppose you could stand at one edge of Andromeda and simply point across it, the way you might point across a lake or a valley, and ask a straightforward question. How long would it take to get to the other side? It sounds like a practical question, almost like travel planning, but once you apply it to a galaxy, it turns into a slow lesson in scale. The moment you try to turn Andromeda's size into time, the distances stop being impressive numbers and become something more stubborn, something that refuses to fit into ordinary thinking. To keep things grounded, it helps to start with what across Andromeda means in the first place. When astronomers talk about the size of Andromeda's visible disk, a commonly used figure is roughly 200,000 light-years from one side to the other. Depending on how you define the edge, you'll see somewhat smaller or somewhat larger numbers, but 200,000 light-years is a useful baseline. That's the bright star-filled disk most people picture, the part with spiral arms and the central bulge. If you include the dimmer outskirts and halo stars, the galaxy extends far beyond that, and if you include the dark matter halo, the reach can approach 1 million light-years across. For travel, those distinctions matter. Crossing the bright disk is one kind of trip. Crossing the full gravitational domain is another, far longer one. So let's begin with the visible disk, because it's already huge enough to challenge the mind, and then we can widen the view gradually. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 second, light could circle Earth about 7.5 times. In 1 year, that speed adds up to roughly 9.46 trillion kilometers. That is not a typo in the sense that it is not meant to be read quickly. It is one of those figures that is best treated as a marker rather than a number to hold in your head. A light year is not something you imagine by picturing kilometers. It is something you treat as a unit that exists because the universe forced us to invent it. So if Andromeda's visible disk is about 200,000 light-years across, then light itself would take about 200,000 years to travel from one edge of that disk to the other. Not from Andromeda to Earth, but across Andromeda internally. The moment you say that out loud, the scale becomes clear in a way a raw number cannot provide. 200,000 years is longer than the entirety of recorded human history by a wide margin. It is longer than the time since humans painted in caves. It is longer than the span of agriculture, cities, and written language combined. And that is how long it takes the fastest thing we know to cross the bright part of one galaxy. Now, light travel time is not the same as travel time for a spacecraft, because a spacecraft cannot move at the speed of light. Anything with mass cannot reach light speed according to our best tested physics. Even approaching a significant fraction of light speed would require energy and engineering far beyond anything humans currently have. Still, imagining different speeds is the most concrete way to translate distance into time. Let's start with a speed that feels familiar in a human way. Imagine travelling at highway speed, about 100 kilometers per hour. That's the kind of speed where you can cross a country in a day or two. It's comfortable, ordinary, and completely useless for interstellar travel, which is exactly why it's a good starting point. It shows you how quickly the scales diverge. At 100 kilometers per hour, in 1 year you would travel about 876,000 kilometers, since there are 8,160 hours in a year. That sounds like a lot until you compare it with even 1 light year, which is 9.46 trillion kilometers. If you divide 9.46 trillion by 876,000, you get roughly 10.8 million years to travel 1 light year at highway speed. 1 light year. Not across Andromeda, not across the Milky Way, not to Andromeda, just 1 light year. And Andromeda's disk is around 200,000 light years across. Multiply 10.8 million years by 200,000, and you land in territory so large it stops being useful as a number. You get something on the order of trillions of years. That is far longer than the age of the universe, which is about 13.8 billion years. So at highway speed, crossing Andromeda is not merely impractical, it is a kind of mathematical joke. You could not do it even if you started before the universe existed, because the universe has not existed long enough. That may sound bleak, but it is also clarifying. It tells you that galactic distances are not very far in the way we mean it here. They are a different category entirely. So let's increase the speed to something that at least belongs to space travel. The fastest spacecraft humans have launched reach speeds on the order of tens of kilometers per second relative to the Sun, depending on the mission and how you define the reference frame. The Parker Solar Probe, for example, has reached extremely high speeds near the Sun, and other spacecraft have achieved high heliocentric velocities using gravity assists. For the sake of a calm estimate, imagine a spacecraft cruising at 50 kilometers per second, which is fast by human standards. 50 kilometers per second is 50 x 60 x 60, 180,000 kilometers per hour. In 1 year, that is about 1.58 billion kilometers. Divide 1 light year, 9.46 trillion kilometers, by 1.58 billion, and you get about 6,000 years per light year. Again, that's per light year. Now multiply by 200,000 light years for a disk crossing, and you get around 1.2 billion years. That's a billion-year journey across the bright disk of Andromeda, at a speed far beyond what any crewed spacecraft has ever achieved. A billion years is an uncomfortable span for any human narrative. Continents shift in a billion years. Species rise and disappear. Star formation changes a galaxy's appearance over that time scale. So even at 50 kilometers per second, you're no longer talking about a trip through a stable environment in any familiar sense. You're talking about moving through a galaxy while the galaxy itself continues evolving around you. You might respond by pushing the speed much higher into the realm of hypothetical future propulsion. Let's imagine you could travel at 1% of the speed of light. That is 0.01c, or about 3,000 kilometers per second. This is wildly beyond current spacecraft capabilities, but it is not forbidden by physics in principle. It is just extremely difficult in practice. At 1% of light speed, crossing 200,000 light years would take about 20 million years. That is already a dramatic reduction from a billion years. 20 million years is still longer than the existence of our species in its current form, longer than the time since many major evolutionary transitions on Earth. But at least it is within the universe's lifetime in a way that feels less absurd. Now imagine 10% of the speed of light, 0.1c. That would reduce the disk crossing to about 2 million years. At that speed, you could traverse the bright disk in a time comparable to the distance between Andromeda and us in light travel terms. 2 million years is still enormous, but now it begins to feel like a timescale used in geology and evolution, not in cosmology. It is the length of time over which ice ages come and go. It is long enough for the night sky to change subtly due to stellar motions. If you go even higher, to half the speed of light, 0.5c, you might think the problem is nearly solved. At 0.5c, the disk crossing time in the galaxy's own frame would be about 400,000 years. That is still vast, but it starts to resemble a time span that humans can at least talk about without stumbling. It is longer than modern humans have been around, but not by orders of magnitude. However, once you start talking about travel at large fractions of light speed, you also have to deal with relativity. Time dilation means that the traveller experiences less time than observers who are at rest relative to the galaxy. At 0.5 c, the effect is noticeable but not extreme. At 0.9 c, it becomes more dramatic. If you could travel at 0.9 c, the disk crossing as measured by a stationary observer would be about 222,000 years, but the traveller would experience less due to time dilation. At 0.99 c, the time experienced on the ship could shrink further. This is where the question can start to drift into science fiction, not because relativity is fictional, but because the engineering challenges become enormous. The energy required to accelerate something with mass to such speeds rises steeply. The problem is not just getting fast, it is surviving the trip. Even in interstellar space, you're not moving through perfect emptiness. There are particles, dust grains, stray atoms. At high fractions of light speed, even a tiny grain of dust becomes dangerously energetic relative to your spacecraft. Shielding becomes a serious issue. Navigation and deceleration become major problems as well. If your goal is to cross Andromeda rather than simply pass through it once and keep going, you also need to slow down at some point. That means carrying or acquiring enough energy to brake, which doubles the challenge. Still, it can be calming to treat these issues as background and focus on the scale lesson rather than the engineering. The scale lesson is simple. Even when you imagine speeds that are far beyond current human capability, Andromeda remains large enough that crossing it takes timescales measured in hundreds of thousands to millions of years, unless you're extremely close to light speed. And that is only for the bright disk. If instead you define across Andromeda as across its full halo, the numbers expand again. Suppose you take 1,000,000 light-years as a rough diameter for Andromeda's extended dark matter halo. Light would take 1,000,000 years to cross it. At 0.1 c, it would take 10 million years. At 0.5 c, it would take 2 million years. Even at 0.9 c, it would take over 1,000,000 years as measured by an external observer. The halo is enormous in a way that makes the disk feel almost compact by comparison. Another way to make this real is to compare it to something we already know. The distance from the Sun to the nearest star system, Proxima Centauri, is about 4.24 light-years. If crossing 4.24 light-years seems challenging, then crossing 200,000 light-years is not just challenging, it is a different kind of problem. It is crossing a span equivalent to nearly 47,000 trips from the Sun to Proxima Centauri laid end-to-end. And each of those short interstellar trips would already be a generational undertaking at anything less than extreme speeds. It also helps to think about what you would encounter during such a journey. People sometimes imagine crossing a galaxy as travelling through crowded star fields, weaving between suns like threading through traffic. In reality, most of the trip would be long periods of almost nothing. Stars are separated by several light-years on average in the disk, often more in the outskirts. The sky from a hypothetical ship would show stars, but they would not be much denser than what you see from Earth, unless you pass through regions near the central bulge where the stellar density rises. If you travelled through the spiral arms, you might pass regions with more gas and dust, where star formation is active. You might see bright nebulae and clusters of young stars. You might see supernova remnants, hot regions emitting radiation. But the journey would not be a constant parade of objects. It would be a slow crossing of a structure that is mostly space, held together by gravity, with matter concentrated in patterns. That brings up a subtle point. Travelling across Andromeda is not like crossing a continent where the landscape remains fixed beneath your feet. In a galaxy, everything is moving while you move. Stars orbit the centre. Spiral arms are density patterns rather than rigid structures. Gas clouds drift and collapse. Over millions of years, the distribution changes. Over hundreds of thousands of years, even the positions of nearby stars shift. So if your trip takes millions of years, Andromeda will not look the same at the end as it did at the beginning. The galaxy's overall structure will still be recognizable, but local details will change. New stars will form, others will die, clusters will disperse. The map you started with would slowly become outdated. This is not because galaxies change quickly, but because your travel time would be long enough to make even slow changes add up. There is also the question of what counts as a cross. A straight line across the disk passing through the center is one definition. A path that avoids the dense central regions is another. A route that follows a spiral arm is another still. Each path has a different environment and different hazards, yet the same fundamental problem remains. The distances are so large that the choice of path changes the journey only slightly in terms of time unless your speed is extremely high. All of this can sound like a wall of impracticality, and if you treat it as a literal travel plan, it is. But as a way to understand Andromeda's size, it is one of the clearest approaches. Converting distance into time forces the brain to stop treating a galaxy as a picture and start treating it as a place with internal scale. It is not just out there, it has width, it has depth, it has enough room that you can measure it in hundreds of thousands of years even at light speed. The calm part of this realization comes from its steadiness. Andromeda's size is not chaotic. It is not an unpredictable sprawl. It is a stable, long-lived arrangement. The distances are consistent. The physics is consistent. The galaxy has been this large for a long time, and it will remain large long after our moment passes. If you let the idea settle, you may notice it changes how you think about the word near. Andromeda is near compared to most galaxies we talk about. Yet inside Andromeda, the distances are so large that even nearby stars within it are separated by years of light travel, scale nests within scale. The local group is a neighbourhood, and within that neighbourhood each galaxy is a country-sized structure in light years, and within each galaxy star systems are islands scattered across enormous space. Time behaves differently once you stop thinking about it in hours or years and start thinking about it as something that flows through a structure as large as a galaxy. Inside Andromeda, time is not marked by days or seasons or even generations. It is marked by motion that takes millions of years to become noticeable, and by changes that require billions of years to fully unfold. When you ask about the scale of time inside a galaxy this large, you're really asking how long it takes for anything meaningful to happen when the distances are vast, the motions are slow, and gravity is patient. The first shift that has to happen is letting go of the idea that time inside a galaxy is experienced uniformly everywhere. Just as distance inside Andromeda varies depending on where you are, time plays out differently depending on what process you're observing. Some things happen relatively quickly, even in a galaxy. Others move so slowly that calling them events feels almost misleading. Consider the motion of stars around Andromeda's center. Our own Sun takes about 225 to 250 million years to complete one orbit around the center of the Milky Way. This span of time is sometimes called a galactic year. In Andromeda, stars at similar distances from the center take roughly comparable amounts of time to complete an orbit. That means that a single full rotation of the galaxy, in any meaningful sense, takes hundreds of millions of years. During one such orbit, entire civilizations could rise and fall on planets orbiting those stars, if such planets exist. Continents could shift, species could evolve or disappear. Yet from the galaxy's perspective, nothing dramatic would have happened. One slow loop, barely different from the last. Move farther out into the disk and orbital periods grow longer. Stars near the outer edges of Andromeda's visible disk can take several 100 million years, or even more than 1 billion years, to complete a single orbit. These stars are moving through space at tremendous speeds, yet the distances involved are so large that progress around the galaxy remains slow. In the halo, time stretches further still. Halo stars often follow elongated, looping paths that can take billions of years to complete. Some may not even have completed a single full orbit since they were captured or formed. Their motion is so gradual that their paths are better described statistically than individually. This immediately tells you something important. Andromeda is not a place where change happens quickly on a global scale. It is a place where structure persists. The galaxy you see today looks broadly similar to how it looked hundreds of millions of years ago, and it will look broadly similar hundreds of millions of years into the future. That does not mean nothing changes. It means change is layered. On small scales, things can happen relatively fast. On large scales, everything takes time. Star formation is a good example of this layering. Individual stars can form over timescales of a few million years. In astronomical terms, that is fast. A dense cloud of gas collapses, fragments, and ignites nuclear fusion. New stars appear, lighting up their surroundings. Yet the conditions that allow star formation to occur in certain regions of Andromeda are shaped by processes that unfold over hundreds of millions of years. Spiral density waves move slowly through the disk, compressing gas as they go. Interactions with satellite galaxies disturb gas reservoirs over long periods. The supply of raw material changes gradually. So while stars can form quickly once conditions are right, the establishment of those conditions is governed by much longer timescales. Fast events are embedded within slow frameworks. The lives of stars themselves span an enormous range of times. Massive stars burn brightly and die quickly, sometimes in just a few million years. Smaller stars, like red dwarfs, can persist for tens or even hundreds of billions of years, far longer than the current age of the universe. In Andromeda, both extremes exist simultaneously. Young, massive stars trace spiral arms and regions of recent activity. Older stars populate the bulge and halo, some having existed since the galaxy's early history. Time inside the galaxy is not synchronized. Different stars represent different eras coexisting in the same structure. This coexistence can make Andromeda feel timeless, even though time is constantly flowing through it. The galaxy contains its past and present at the same time. Ancient stars orbit alongside newly formed ones. Remnants of past mergers drift through the halo, while fresh gas clouds collapse in the disk. On longer timescales, entire structural features evolve. Spiral arms are not permanent fixtures. They come and go over hundreds of millions of years, reshaped by gravitational interactions and internal dynamics. The central bulge can grow through mergers and through the gradual inward migration of stars and gas. These changes are subtle when viewed from moment to moment. Over tens of millions of years, they become noticeable. Over billions of years, they can reshape the galaxy's appearance. Mergers operate on the longest and most dramatic timescales. When Andromeda absorbs a smaller galaxy, the process can take billions of years from first approach to final settling. The initial gravitational interaction stretches the smaller galaxy, creating streams of stars. Over time, those stars are dispersed throughout the halo, slowly mixing with Andromeda's existing population. Even after a merger is technically complete, its effects linger. Stellar streams remain coherent for billions of years before fully blending into the background. These streams are time markers, evidence of events that occurred deep in the past, still readable in the present. The dark matter halo evolves on similarly long timescales. Its shape changes as mass is added through mergers and accretion. Its interaction with neighbouring halos, including that of the Milky Way, unfolds over billions of years. The eventual merger between Andromeda and our galaxy will be governed primarily by the behaviour of these halos long before the visible disks touch. This brings in another aspect of time inside a galaxy this large: anticipation. Many of the most significant future events are already in motion, even though they will not reach their most obvious stages for billions of years. The slow approach of Andromeda and the Milky Way is happening now, yet it will remain imperceptible for countless generations. From a human perspective, this can feel almost paradoxical. How can something be happening if nothing seems to change? In galactic terms, happening does not require immediacy. It requires continuity. Motion measured in kilometers per second can still take millions of years to matter. Time also behaves differently when measured by energy rather than by clocks. Gas cooling in Andromeda's halo may take billions of years before it becomes dense enough to form stars. Heat dissipates slowly in such thin environments. Gravity works steadily but without urgency. In this way, Andromeda functions almost like a memory structure. Its present state contains records of processes that unfolded over vastly different timescales. By studying its stars, gas and motions, astronomers can reconstruct events that occurred billions of years ago. The galaxy remembers its own history and its structure. This memory is not stored neatly. It is encoded in distributions, velocities, compositions, and arrangements. Reading it requires patience and interpretation. Yet the fact that it exists at all is a consequence of slow time. Rapidly changing systems erase their past. Slowly changing systems preserve it. From the inside, if you were somehow able to exist within Andromeda across vast spans of time, your experience would be one of continuity rather than drama. The sky would change slowly. Star positions would shift gradually. The galaxy would feel stable. That stability does not mean stagnation, it means resilience. Andromeda has endured countless internal and external influences over its lifetime. It has grown, merged, lost material, and reshaped itself, all without falling apart. The scale of time also reframes the idea of age. When we say Andromeda is billions of years old, we are compressing an immense history into a single phrase. During that history, the universe itself changed. Early Andromeda formed when the universe was denser, more compact, and filled with more raw gas. Over time, conditions shifted. Star formation slowed. Structures matured. Even now, Andromeda is not finished. It is mid-story. Its future merger with the Milky Way will produce a new galaxy with its own long timeline. That future system will have its own internal timescales, its own rhythms of motion and change. Another way to think about time inside Andromeda is to consider how long light takes to cross internal distances. Light crossing the galaxy's disk takes hundreds of thousands of years. That means that different parts of Andromeda are, in a sense, slightly out of sync with one another observationally. Light leaving one edge arrives at the other long after local conditions have changed. Within the galaxy, however, this delay does not matter for dynamics. Gravity acts effectively instantaneously on these scales for practical purposes, maintaining cohesion despite light travel times. Still, the existence of such delays highlights how stretched the galaxy is across both space and time. The stars you see in one region of Andromeda are not aware, in any meaningful sense, of what is happening simultaneously on the far side. Their interactions are local, guided by gravity that reflects the overall mass distribution, rather than moment-to-moment changes. This separation of influence and information is another reason galaxies evolve slowly. Feedback takes time to propagate. Effects are averaged over long periods. Extremes are smoothed out. For someone listening quietly, this immense scale of time can be strangely comforting. There is no rush built into the system. Nothing in Andromeda demands immediate resolution. Processes unfold at a pace that makes urgency irrelevant. Human life exists at the opposite extreme. We experience time as fleeting. Moments pass quickly, decisions feel pressing. Against the backdrop of a galaxy, this contrast becomes clear, but not necessarily distressing. It can be grounding. The galaxy does not hurry because it does not need to. Its size ensures that change is gradual. Its mass ensures stability. Its time is deep and wide. Understanding the scale of time inside a galaxy like Andromeda also helps explain why astronomical observations often focus on snapshots. We cannot watch a galaxy evolve in real time. Instead, we infer its evolution by studying many galaxies at different stages, spread across the universe, effectively using distance as a time machine. Andromeda occupies a special place in this approach because it is close enough to study in detail and old enough to have accumulated a long history. It shows us what a mature spiral galaxy looks like after billions of years of gradual change. As this idea settles, another perspective emerges naturally. If time inside Andromeda is measured in hundreds of millions and billions of years, then human presence, even on cosmic timescales, is brief. Yet the fact that we can understand and describe these timescales at all is remarkable. There is no need to draw conclusions from that contrast. It does not require meaning or interpretation. It simply exists. A large galaxy operates on long time scales. A small species operates on short ones. Both are part of the same universe. After considering time inside Andromeda, the next thought often turns toward our own place beneath such a universe. How does living under structures this large and this old change perspective? What does it mean to rest beneath a sky shaped by galaxies that operate on timescales far beyond human experience? There is a point after thinking about distances measured in light years and times measured in millions or billions of years, when the mind naturally slows down, not because it is overwhelmed, but because it runs out of reasons to hurry. When the universe is this large, urgency loses its grip. That is the place where it makes sense to pause, not to conclude anything, but simply to rest beneath the scale that has been unfolding. Right now, wherever you're listening from, you are physically very small in the universe. That statement is factual, not philosophical. Your body occupies a tiny region of space on a planet that itself is small compared to stars, which are small compared to galaxies, which are small compared to the vast structures that galaxies form together. This hierarchy can sound diminishing at first, but it does not have to feel that way. Smallness in this context does not imply insignificance, it simply describes proportion. The ground beneath you, whether it's a bed, a chair, a floor, or something else familiar, exists within layers of structure that extend far beyond what you can sense. Beneath Earth's surface lies the planet's interior. Beyond Earth lies the solar system. Beyond the solar system lies the Milky Way. Beyond the Milky Way lies Andromeda and countless other galaxies. None of these layers require your attention to exist. They continue regardless. Resting beneath a universe that is much bigger than us does not mean submitting to something oppressive or overwhelming. It means recognizing that the universe does not depend on constant engagement. It does not need to be managed or interpreted at every moment. It simply unfolds. One of the quiet comforts of astronomy is that it places human concerns into a wider context without dismissing them. Your experiences still matter to you. They still shape your days and nights, but they do not have to carry the weight of the entire universe. That weight is already distributed across immense structures and timescales. The stars above you tonight, whether you can see them or not, are doing what they have always done. They burn fuel in their cores. They orbit galactic centers. They drift relative to one another over millions of years. None of this accelerates because you're watching, and none of it slows down because you're resting. Andromeda specifically continues to exist as it has throughout this entire conversation. Its stars are moving. Its halo is interacting subtly with the Milky Way's halo. Its future merger with our galaxy remains scheduled not by intention, but by gravity. Nothing you think or feel alters that trajectory, and that can be oddly reassuring. There is no responsibility attached to understanding the universe. You're not required to hold its scale in your mind or to extract meaning from it. Understanding can simply be something that passes through, leaving behind a sense of spaciousness rather than obligation. Rest in this sense is not about stopping thought entirely. It is about allowing thought to expand without tightening. When the subject is this large, there is no edge you need to reach, no conclusion you need to arrive at. The universe does not demand comprehension to continue functioning. On a planet like Earth, much of life is shaped by cycles that feel immediate. Day and night, work and rest, seasons. These cycles are meaningful because they operate on timescales that intersect with human biology. Galaxies operate on cycles that are so long they barely intersect with individual lives at all. This separation of scales means that the universe provides a stable backdrop. While human affairs can feel chaotic or unpredictable, the large-scale structure of the cosmos changes very slowly. That slowness creates a kind of continuity that can be leaned on, even if only indirectly. Looking up at the night sky has always had this effect on people. Long before anyone knew what a galaxy was, the stars still suggested permanence. They returned night after night, largely unchanged. Even now, knowing that they are moving and evolving does not remove that impression. The changes are simply too slow to disturb it. Andromeda contributes to this sense of continuity in a subtle way. It is there, faint and distant, a reminder that the universe extends beyond immediate surroundings. Its light has been travelling toward Earth for millions of years, indifferent to borders, calendars, and individual concerns. When you rest beneath a universe that is much bigger than you, it can help to notice what does not happen. The universe does not rush you. It does not demand answers. It does not evaluate how well you understand it. It allows you to exist within it without expectation. This allowance is not granted conditionally. It is built into the nature of things. Stars do not need permission to shine. Galaxies do not need justification to exist. Planets do not need approval to orbit. You do not need to earn your place in this structure by understanding it fully. Sometimes, thinking about cosmic scale brings up a sense of insignificance. That reaction is understandable, but it is not the only possible one. Another response is relief. If the universe is this large, then not everything depends on any single moment or decision. Mistakes do not echo forever across the cosmos. Worries do not alter galactic orbits. There is room for imperfection because there is so much room, period. The physical smallness of humans coexists with a unique capacity for awareness. You're able to think about Andromeda at all. You're able to imagine distances you will never cross and times you will never experience. That awareness does not make you larger in a physical sense, but it does place you in relationship with the universe in a distinctive way. That relationship does not require constant engagement. Awareness can rest. Curiosity can quiet down. The universe remains whether you're actively thinking about it or drifting towards sleep. As this narrative slows, it is worth noticing how the earlier questions have softened. How big is Andromeda? How far away is it? How long does it take to cross it? How does time behave inside it? These questions have not been answered in a way that closes them off. Instead, they have expanded into a sense of scale that does not need to be resolved. There is no final number that makes Andromeda feel fully graspable. There is no single comparison that makes its size intuitive forever. Scale is something the mind revisits gradually, adjusting a little more each time. Resting beneath this scale means allowing that adjustment to pause. You do not have to integrate everything right now. The universe is not a puzzle with a deadline. The night sky, whether visible or imagined, can act as a kind of ceiling that does not press down. It does not confine. It opens outward. Even indoors, even with eyes closed, the awareness of that openness can linger. Earth continues rotating beneath that sky. The Milky Way continues orbiting its center. Andromeda continues its slow approach. All of this happens without interruption, regardless of whether anyone is watching. This continuity can be a place to set down mental weight. You do not need to carry the universe. It carries itself. If thoughts drift, that is fine. If attention fades, that is fine too. The scale you've been exploring does not disappear when focus softens. It remains in the background, steady and untroubled. There is no need to draw meaning from the universe being bigger than us. Meaning is not a requirement for existence. It is something humans add when it feels useful, and set aside when it does not. For now, it is enough to recognize that you are part of a system that is stable on scales far beyond daily experience. That stability does not solve personal problems or race difficulty, but it does provide context that can make those difficulties feel less absolute. The universe is not watching, it is not judging, it is not waiting for understanding, it simply continues. As awareness settles, the idea of Andromeda can remain present without effort, not as an object to analyze, but as a reminder of space, time, and patience, a galaxy that exists quietly regardless of attention. Nothing about this moment needs to be finished. The universe does not move toward conclusions, it moves through states, one after another, slowly and without urgency. You are allowed to rest within that motion, knowing that scale does not demand action, and that being small in a large universe is not a problem to solve, but a condition that has always been true and will remain so quietly as everything continues on its way.